Asteroids are no longer just small rocky worlds floating in space. They have become new economic opportunities and places strategic to space exploration.
There's almost unlimited resources on the asteroids. There are many different types, and they each contain different resources that we could use.
Most of them are made of metals like iron, nickel, or precious metals like gold or platinum that are very valuable. However, the most valuable material on asteroids is the simplest element: water. In the near future, we could use asteroids as pit stops to refuel spacecrafts en route to deep space with propellant made out of water.
That is where the value of asteroids really lie, as they become gas stations or pit stops or stepping stones in our process to explore further and further into the solar system.
In the last few years, space has become of interest not just to the public sector, led by national space agencies, but also to the private sector, resulting in an unprecedented industrial revolution. Several companies have plans to explore and use resources from asteroids. Most of these companies are based in the USA. However, there is a small country in the center of Europe that is playing a key role in this emerging sector: Luxembourg.
Luxembourg have become very interested in asteroid mining. They're bigger in space than they are on the ground.
But to make asteroid mining economically feasible, we need to solve some technical challenges.
The cost of sending a spacecraft to the asteroid belt used to be about the same as if the spacecraft were made of pure platinum.
Once those challenges have been overcome, we might start to dream of asteroids as our new targets, small, isolated worlds that could play a key role in future space economy.
I think there's a great analogy to the 1800s gold rush in the western United States for the economy of the future for the late 21st century out there in space.
You're looking for stuff that you want, and specifically, if you're going to turn an asteroid into a place for people to live.
We are about to be witness to a whole space industrial revolution that will see asteroids become our next frontier. In the last few years, several missions to asteroids have shown us that they have many resources that could be useful to us.
The advantages of asteroids are that they have a lot more favorable chemistry. The components that the asteroids are made of are a lot more of the things that we find valuable.
There is one type of asteroid, the C-type, also known as the carbonaceous or chondrite asteroids, that are the most abundant and have not just hydrocarbons, but also a key element for the future space industry: water. Water is an extremely valuable resource for several reasons. It will be necessary for resupplying. Astronauts could use asteroids as stops to refill the water tanks of spacecrafts in long, deep space journeys to destinations like Mars.
By having water on practically everywhere around the solar system, because there's millions of these asteroids floating around, you have the possibility to use water not just for humans. It's good for drinking. Water can be used to obtain oxygen. You can use them to shield you from radiation, to grow plants, whatever you need. But the real importance of water on asteroids is because you can use them as a means of energy, as a propellant.
You can just heat the water to steam and then use that as a rocket, a steam rocket. And that's a way to get around space. But another way is to take the water and split it by electrolysis into hydrogen and oxygen, and then then use that in a liquid hydrogen, liquid oxygen rocket, and that's the most powerful chemical rocket we have today.
So in a way, water becomes, as we say, the oil of space. Because once you have that propellant, that will help you to move around the solar system, get you to much further destinations. You will be able to now refuel, so you don't have to bring that fuel from Earth. And so that allows you to have larger rockets, larger payloads, and truly they become stepping stones, or sometimes they call it pit stops along the way.
Several missions have recently explored or are exploring several C-type asteroids, as the Hayabusa 1 mission from JAXA, the Japanese Aerospace Exploration Agency, or 2 ongoing missions, NASA's Osiris Rex mission and JAXA's Hayabusa 2. All of these missions have the peculiarity of being sample return missions, which means that probes will grab some asteroidal material and will return it to the Earth for its later analysis. These samples will be extremely useful to know much more about the real composition of asteroids and will allow us to study their real potential as resources. There's another type of asteroid, the M-types, or metallic, which are made of nickel, iron, iridium, platinum, gold, or other precious metals, either pure or mixed in different proportions with stone. Those asteroids might be used as an endless resource of materials and minerals.
They also are important because some of those asteroids, the metallic types, hold important metals that are used for a variety of things, for construction, like iron and nickel, and also the valuable platinum group metals. So once you have those metals, now you have the material that you need to develop manufacturing things like, for example, tools or spare parts, or even large construction material for satellites.
There are even some asteroids like Psyche, which are made almost entirely of metal that could eventually become very interesting targets for the future asteroid mining industry, as the metals are on the surface and there's no need to dig deep to extract them, as happens here on Earth, greatly simplifying the mining process. The NASA mission to Psyche, planned for 2022, will allow us to know more about this unique metallic world. All the resources we can extract from asteroids might be really useful for industrial purposes in the near future, once the space industry revolution has finally kicked off. Things have been changing very fast in the space industry in the last few years, thanks to the rapid growth of private space companies, the real game changers in the space industrial revolution.
I think we are entering a new era when private entities are taking a bigger role in space than they did before. They're creating a kind of more commercial market for new people to work and live in space that we didn't have before. And that's driving what I think is going to be a new era in space exploration that is less directly tied to government programs, but more commercial activity in space.
This new space industry has several main drivers. On the one hand, improvements in launch systems, sensors, and other input and innovations, such as the small-sat architecture, are driving down costs.
The new space concepts, this idea that there's this environment out there, a potential environment for economic investment and economic return that is effectively boundless. We live on a planet with limited resources. Space around us, the solar system around us, represents economic resources, mining, mineral resources that are effectively boundless.
The combination of decreased costs and increased capabilities of smallsats opens up new use cases, industries, and applications for businesses. All of these have led to the democratization of space, as it will be no longer just territory exclusive to huge national public space agencies, but also for any big or small private companies eager to invest in space.
That is what is pushing not just the governments, but the private industry and the rest of the world, not just the space-faring nations, but the rest of the world, as you're seeing now, is interested in entering this new phase of space. It will be not just for exploration, not just for gathering scientific knowledge, but to truly start using space to help us in commercial activities and economic ventures.
The key driver has undoubtedly been the increasing development of fully reusable rockets that will dramatically reduce the costs of launching. The main reason that space has been, up until now, an industry only affordable to huge space national public institutions such as NASA, ESA, Roscosmos, Russia, or JAXA, Japan. Private companies like SpaceX or Blue Origin, led by multi-billionaire entrepreneurs like Elon Musk or Jeff Bezos, are the ones that are investing most heavily in developing techniques to reduce launching costs. The development of more capable and increasingly smaller satellites is another of the drivers of this coming industrial revolution. Private companies like Planet or OneWeb are leading the production, launch, and control of these nanosats, which will radically improve our network communications, broadcasting systems, geolocation systems, or Earth observation. In addition to the aerospace industry, this space industrial revolution will also transform communications, the internet, tourism, the energy industry, manufacturing, and mining.
There's other opportunities in space entertainment and on-orbit manufacturing, things that will also create revenues and activity and create a demand for an on-orbit facility. I expect all of this to happen in the next 5 to 10 years.
The mining industry will focus especially on the moon and on asteroids as the easiest targets for obtaining resources such as minerals, metals, or water. Asteroid mining, which has belonged to the realm of science fiction until now, could become a reality in the near future. We may be witness to a 21st century gold rush.
The real estate plays when we start launching lots of people to space. It's going to be the manufacturing that we can get going on orbit. It's going to be all of the things that we can do, and you're going to need everything you can possibly imagine on Earth. We're going to need that in space. That's going to create an incredible amount of value. That's going to engage a lot of people.
There are two places in the world that concentrate most of the companies responsible for this revolution: California in the United States and Luxembourg, a very small country in the heart of Europe. Luxembourg is a very particular case. It could become the Silicon Valley of asteroid mining. This tiny state took a gamble on the space industry and nowadays hosts the SES, Société Européenne des Satellites, the world's leading satellite operator, with a fleet of about 50 satellites. This country is one of the main accelerators of this emerging space industry revolution.
Luxembourg have become very interested in asteroid mining. They're a fascinating little country, and they're a very little country. But in the 1980s, they helped to set up some of the first commercial telecommunication satellites. And now the largest telecommunication satellites in the world are from Luxembourg. So they're bigger in space than they are on the ground.
The goal of the Luxembourg government is to put into place an overall framework for the exploration and commercial use of resources from celestial bodies such as asteroids. An adventurous and unproven enterprise like space mining requires financial backing, legal frameworks, and favorable regulatory structures to allow the work to even take place. Luxembourg has expertise in this area, given its experience in the mid-1980s with the commercial satellite industry.
They're smart enough to know the financial industry, and they're a fairly concentrated economy in a couple of sectors. So they're now aggressively looking for other wins they can make. How can they get ahead of the game? And so they've realized asteroid mining it's not just about the regulatory environment. I mean, it's easy enough for them to write favorable regulations so that it makes sense, but they also want to invest to move that forward and really cement their position in the asteroid mining industry.
Asteroid mining could become a big industry within the next decade, depending on how we solve the many technical difficulties involved. The first difficulty is to know which asteroids are the most interesting for mining purposes, as there are asteroids spread all over the solar system.
To know which asteroids to go to, we work with collaborators who have been studying meteorites and remote observation of asteroids. And from our observations, we can determine which type of asteroid it is. And the meteorites tell us kind of the range of possibilities of the mineralogy of those asteroids.
The data gathered by NASA, ESA, the European Space Agency, JAXA, the Japanese Aerospace Exploration Agency, and other space agencies in the last few years on near-Earth asteroids, the most easy accessible, will facilitate the selection of the best targets for asteroid mining companies. Another difficulty would be to decide the best way to mine, whether to bring raw asteroidal material to Earth for use or to process it on-site to bring back only processed materials and perhaps produce propellant for the return trip. Or even to transport the asteroid to a safe orbit around the Moon, Earth, or to the International Space Station. This could hypothetically allow for most materials to be used and not wasted.
What makes asteroids unique and different from other bodies like moons or planets is that they are so small that their gravity is practically zero. That low gravity is good for a couple of things. That makes it easier to get to them. The energy that you need to get to them is lower than even to get to the Moon or Mars. So they are easily accessible energetically, not necessarily on time. They may be far away, but it's easy to get to them in energy. But one thing about the very low gravity of them is that all the techniques that we have learned on how to mine or extract materials here on Earth are quite different when you get to an asteroid. You no longer have that gravity that can keep an excavator on the ground and the traction that you need to move around. These things will tend to float. So you have to design different techniques how to extract this material.
At the Center for Space Resources of the Colorado School of Mines, one of the most renowned space research centers in the world, different experiments have been developed to test the specific techniques intended for asteroid mining. The scientific team uses a sophisticated vacuum chamber to recreate the extreme conditions in space more accurately.
Here at the Colorado School of Mines, we focus on creating environments in which we can test mining equipment in space, or potential mining equipment in space. We have a large vacuum chamber in which we can create a low pressure environment that's similar to what we have in space. We can place simulants of asteroid surfaces that are dusty and will create a dust cloud as we work with them. We can pull a vacuum on it to bring the pressure down to a low enough that it's simulating space. And we can do other things like chill it to very cold temperatures as you might have in space. So it mimics the conditions in space.
To recreate the conditions of an asteroid surface for asteroid mining tests with greater accuracy, scientists use simulants, composed mainly of silicates such as feldspar and quartz. Most of the simulants are similar to materials we would find in carbonaceous chondrite asteroids, which are the most abundant and most closely studied. Their composition is based on a variety of data sets, including laboratory analysis of meteorites, observation of bolides, remote sensing of asteroids, data from asteroid missions, and scientific modeling. Thanks to all of this data, scientists have been able to produce the simulants with great accuracy in mineral content and particle size.
What we have here are Asteroid simulants. We're making simulants of asteroids. We get the raw material for these simulants from our collaborators at the University of Central Florida, who are experts in the mineralogy of asteroids. And then we're making asteroid surfaces. We're creating a simulant of the asteroid surface. This is one example that kind of mimics a large boulder on an asteroid. These here are smaller boulders or cobbles. Friable because asteroid surfaces have rubble strewn across them, of varying sizes from boulder size to hand size to little pellets.
When it comes to developing mining techniques for asteroids, drilling and anchoring are two processes that have to be closely studied due to the peculiar properties of these small celestial bodies. In the case of drilling, the microgravity plays an important role, as the almost total lack of gravity creates different conditions for mining on Earth.
One thing to understand about asteroids is that the gravity on asteroids is very low. In a lot of processes we use for mining on Earth, we use the weight of a vehicle to hold it down so you can dig. But you can't do that on an asteroid.
The data gathered in the microgravity research in core drilling will provide conclusions on the efficiency of drilling to collect asteroid material, as well as the dangers presented by having loose debris so close to the drill operator. After collecting data on the exit patterns of the debris in a microgravity environment, an appropriate capturing device can be designed to ensure maximum collection. Developing a device that collects excess debris will also decrease the potential for damage to the drilling device.
What you can do is build systems that grip the asteroid or harpoon it and create an anchoring point onto the asteroid. That then gives you a way to hold onto the asteroid while you use some other device to scoop up the parts of the asteroid and move it into some processing system, like cut up a metallic asteroid so that you can take in metals and refine it within some microgravity refining system. We can study the methods you might use to anchor to asteroids. Might look a little bit like a drill or a harpoon, or even just kind of gripping devices that hold onto the surface of an asteroid. And we want to study them, or want to determine ways to design anchoring equipment so that it provides enough grip so that you can then scoop and scrape and cut the surface of an asteroid.
Considering that the surfaces of many asteroids are made of boulders, pebbles, and little grains, anchoring processes could eventually be really difficult. That's why it's useful to do testing to study the best way to penetrate and anchor to that surface.
What we're basically doing is penetration testing. So what we're doing is we're taking this probe and we're pressing it down into the regolith, into this simulated regolith, because it's made from stuff here on Earth to simulate what we would find on the asteroid. And when we press it down in, we measure the forces that occur both in the upward in all different directions, as well as the torques. The reason for doing that is to kind of understand if we were to land on an asteroid and we wanted to press into the soil, say we want to anchor, or we want to extract water, or we want to build a habitat, or we even just want to understand how the surface of the asteroid is going to move or react when a meteor hits it. We use liquid nitrogen to freeze them because the surface of an asteroid could get as cold typically as 35 Kelvin. We've sealed the liquid nitrogen inside this. What it is basically, it's a probe that can move around in 6 different directions. So it can move in X, it can move in Y, and it can move up and down in the Z direction. An auger, so it has flutes that run around it. Those flutes allow material to travel up, so it's sort of like your typical drill bit that you would, or like a screw that would go into a piece of wood or anything like that.
This test analyzes the forces involved when drilling or anchoring on a rocky surface which would be useful for the future asteroid mining techniques. One of these techniques is surface mining. On some types of asteroids, material may be scraped off the surface using a scoop or auger, or for larger pieces, an active grab. There is strong evidence that many asteroids consist of rubble piles, making this approach possible. Another technique is shaft mining. A mine can be dug into the asteroid and the material extracted through the shaft. This requires precise knowledge to engineer accuracy of astrolocation under the surface regolith and a transportation system to carry the desired ore to the processing facility. The magnetic rake is one intended for metal asteroids. Asteroids with a high metal content may be covered in loose grains that can be gathered by means of a magnet. The question now is whether asteroid mining nowadays is really a feasible industry if we think of it as a mining industry that provides resources for the Earth.
The cost of sending a spacecraft to the asteroid belt used to be about the same as if the spacecraft were made of pure platinum. So it didn't seem to make sense to go out and get diluted platinum from something that cost you so much to send out there.
Nowadays, the most viable option is to mine and process the resources in situ. As with our present technology, the cost of sending a spacecraft and returning it fully loaded back to Earth would be extremely high.
What is more attractive is to use the resources from that asteroid to use it in space. That makes it more economically feasible because bringing it from Earth is extremely expensive. Bringing water from Earth, bringing the iron and the nickel from Earth is very expensive. So then it becomes economically feasible to extract the resources from the asteroid.
Maybe in the future, if we are able to radically reduce the cost of space missions, it could become feasible.
In the asteroid belt, there are orders of magnitude more materials out there than we've ever imagined. So what you have is companies that can get very excited about claiming these future sources of mineral wealth that will eventually become starships and space colonies.
That dream of space colonies on asteroids might not be so far in the future. We now know that there are asteroids made almost entirely of metal that could potentially become an almost endless resource for industries on Earth in the future.
The existence of platinum group metals was probably the very first resource that attracted interest from companies to go and extract those metals from asteroids. Because of their high value on Earth, there's plenty of platinum on those asteroids. In fact, it has been said that an asteroid a couple of kilometers in diameter or in size has more platinum than has ever been mined and probably will be mined in the next 50 years on Earth. The problem again is it economically feasible to go after that platinum? Is extracting the platinum from Earth more expensive than on asteroids? Not at this moment. The amount of money that you need to launch a rocket to get there to extract the platinum at this point is not competitive. But again, at some point, it may become so hard to obtain the platinum from Earth that it will make sense to actually go to an asteroid to do that. The other thing to consider is the moment you start bringing those large amounts of platinum to Earth, the price of the platinum will just collapse immediately. All of a sudden, you will have all this metal available that it changes completely the price that we put on this. Obviously, if there's more demand for it, if now that we have more and we can use it in many more applications, then it will make it much more attractive to go after them.
This emerging industry is about to kick off. Undoubtedly, the key game changers are asteroid mining companies that are investing mainly in the development of technologies to make this industry economically feasible. Among the asteroid mining companies, there were two that led the race until recently: Deep Space Industries and Planetary Resources. However, due to the low feasibility of the mineral extraction, they are now in a redefining process. In addition to those, there are other asteroid mining companies, each focusing on specific aspects of this industry, such as the production of propellant from water located in the asteroids, the development of robotics, or the search for the right targets. One of them is TransAstra.
TransAstra has a business plan that's focused on extracting rocket propellant from asteroids. You could call that asteroid mining if you want. And then using that rocket propellant to fill refueling stations in space, to refuel NASA spacecraft and private sector spacecraft. For NASA, it would be refueling spacecraft that are taking astronauts on mission of exploration. For private sector, we can refuel space tugs that deliver satellites to their destination orbits.
TransAstra is a new kind of aerospace company intended to contribute to the development of the concept of the transcontinental railroad of space. Their vision is for humanity to become a spacefaring species homesteading the solar system.
We can build the transportation network. It's kind of like the transcontinental railroad of space that will make it possible for industries to go in space for a profit.
Their ultimate goal is to turn thousands of asteroids into refueling stations for NASA and commercial spacecraft, opening the frontier for NASA human exploration and commercial industries beyond imaging satellites and telecommunications. They aim to lead the work in supplying services for 21st century industries of asteroid mining, space solar power, space tourism, and manufacturing in space.
That is going to create the greatest industrial revolution in the history of mankind. And we're standing right here at the moment in history when it's about to happen.
The company has a clever mining technique called optical mining that benefits from the solar power to mine the water on asteroids, water to be used as propellant.
One of the best energy sources we have in space is the sun, and that's one way we can use that is by building reflectors that concentrate sunlight to extract and process materials in space. An example of this is a technique called optical mining that is invented by TransAstra and Joel Sercel. We are collaborating with TransAstra to help understand the basic process of concentrated solar interaction with minerals of C-type asteroids.
TransAstra has invented a process that we call optical mining. Optical mining is an approach whereby highly concentrated sunlight is focused onto the surface of an asteroid or other volatile containing body. The highly concentrated sunlight heats and thermally fractures, means it breaks up the surface. So you have the surface of the asteroid or other water-containing extraterrestrial body. The highly concentrated light hits the surface, and as it heats the surface, it fractures it due to the heat. What's really exciting is that the little particles of the broken surface then individually heat up very fast, and all you have to do to get the water and other valuable compounds out of the asteroid is heat it up. The water comes out as vapor. That vapor actually cleans the surface and exposes the next layer of surface and for the sunlight beam to fracture, and it's a continuous process.
The optical mining technique has been tested in vacuum chambers at the Center for Space Resources of the Colorado School of Mines. They use hydrated mineral-type simulant, similar to the material found on the surface of an asteroid.
I have the chamber itself, and that makes it a vacuum and allows me to put in samples and make them hot or cold, depending on the kind of test that we're doing. Then I have a lamp on top of it, and that allows me to have sunlight focused down, or simulated sunlight focused down onto my sample. And then inside the chamber, I have samples of many different kinds. We will get the light out using just sunlight. So we will concentrate it down to a spot, and a column of water vapor will rise from the surface. So this will probably be the first technique that people use when they're gathering space resources. So after the ice on top of the regolith turns into steam and is sublimated, and it's going to form a little cloud, we're going to take a tent and put it on top of this cloud. The tent is going to be colder than the ground underneath, and in this situation, whenever something is the coldest, that's where the ice will stick.
Transastra is developing an innovative mission concept called APIS, an acronym for Asteroid Provided In Situ Supplies, that includes an autonomous spaceship that will be launched on spacecrafts to reach asteroids.
So what we're going to do is we're going to build a spacecraft that's about the size of a pickup truck and launch it out to an asteroid that's about the size of a house. And then this spacecraft that's about the size of a pickup truck will have inflatable structures, and it'll have a bag that it uses to inflate and then enclose the asteroid. And then the solar concentrators will pump sunlight in, and then through the optical mining process, we'll excavate the asteroid, extract the water, and freeze the water in ice bags. So this honeybee mission, as we call it, will take about 6 months to get to the asteroid. It'll do mining for about 3 months, and then it'll take 6 months to get home, and it will bring back 100 tons of ice. And that's the first small industrial scale mission to bring back an economically important quantity of rocket propellant that can change the economics of space. And we think that that will launch a gold rush in space to harvest asteroid material and also material from the lunar poles. And that will make it so inexpensive to operate in space that it will become practical to do things like build solar power stations in space where the sunlight is much more accessible, much more consistent, much more cost effective if you can launch into space inexpensively enough.
When it comes to benefiting from asteroid resources, one of the greatest challenges is knowing which are the best targets among the thousands of asteroids floating in space. Aten Engineering is a company focused on that field. Their goals are to develop technical solutions for the detection, discovery, follow-up, and characterization of near-Earth asteroids.
We're still working to find some of these bodies with our telescopic surveys, and it may actually take a next generation of telescopic surveys, or possibly a space-based telescope specifically designed to find these kinds of objects.
Up to date, more than 10,000 near-Earth asteroids have been discovered. It's not an easy task to find and to follow them up. But thanks to the Minor Planet Center data and tools, Aten Engineering has been able to study and track those objects. The biggest challenge is to characterize them in terms of size, rotation periods, and spectral composition. Until now, less than 10% have been well characterized. It's estimated that with present technology, it will take about a century to study the entire known population.
We use telescopes to look at the spectra of asteroids, and in the spectral signature you can see different things that tell you what it might be. So you can determine if it's a metallic asteroid, or a stony asteroid, or a carbonaceous.
They are now focused on developing accessible technology for characterization to keep pace with discovery. They are working on quick visible spectroscopy and fast cadence light curves that could be obtained with a telescope in just a few days, as well as in long arc astrometry to be used for phase curves that should take months. All of these would undoubtedly accelerate the rate of characterization of near-Earth asteroids, which would help to analyze their potential as resources for mining purposes.
I'm really excited about asteroids, the near-Earth asteroids in particular, as targets for future human and robotic exploration.
Other companies like Off-World are focused not on the study of the asteroid's properties, but on the development of robotic devices to mine autonomously. Their ultimate goal is to create a squad of autonomous robots working under human supervision on other planets and asteroids, which will allow human beings to spread beyond Earth.
While these little asteroids offer us a lot of benefits to go to as targets, there are still a lot of challenges involved with going to a little asteroid like that.
The environment out there is extremely harsh. Human settlers will have to cope with long, deep space journeys, lethal cosmic radiation, zero or lower gravity, or artificial atmosphere. Off-World thinks the best way to minimize the risks of establishing a permanent and sustainable settlement on other planets would be to have a local robotic army that would be in charge of the hard work. Building landing pads, excavating underground habitats, extracting water ice and materials, making drinkable water, breathable air and rocket propellant, manufacturing basic structures and solar cells, producing electricity, eventually replicating themselves. As the asteroid mining industry grows, thousands of mining robots would be needed everywhere. These robots should be small and robust enough to survive launches on rockets, solar electric powered. Extremely adaptable to work in a wide range of environments on asteroids, the Moon, or Mars without a major redesign. Autonomous and fast learning to survive without on-site human supervision, and modular and reconfigurable to maximize the reuse of launched hardware. The robots should also have self-replication capability using local resources and should be able to manufacture the first off-world computer chips, closing then the robotic self-replication loop. All these asteroid mining companies are now leading a race that could push human beings beyond their natural frontiers to colonize these small, mysterious, rocky worlds in the near future. The potential colonization of asteroids is not an easy task at all, as they are very harsh environments for us, without any shielding from cosmic radiation, as they have no atmospheres or magnetospheres, with extremely low gravity and with a very high chance of collision with other celestial objects. The two main reasons that justify moving off Earth to asteroids would be to benefit from their almost unlimited resources, as well as their colonization as a risk mitigation strategy to ensure the long-term survival of our civilization in case of a planetary catastrophe.
We really want to get the asteroids that are closest to Earth's orbit. There's enough material in those near-Earth asteroids to support maybe 100 billion people living in Earth orbit. There's 1 million times more material in the main asteroid belt. So after we've got people to orbit, we're using this material to live and work and build cities, we can expand to a huge civilization circling the sun. That's pretty exciting.
You're looking for stuff that you want, and specifically, if you're going to turn an asteroid into a place for people to live, you want the kinds of things that would support life. Like especially you would want a certain amount of water. You would want components that you could turn into soil for a greenhouse so that you could grow your own food. You would want sufficient metal concentrations that you could make your own building materials from the base metals. You would want enough precious metals that you could export precious metals to sort of feed yourself and have things to trade with other asteroid colonists or with the moon people or the earth people or whatever.
Throughout our history, opening new frontiers has thrilled generations of explorers and pioneers. Asteroids could be considered the next frontier. The fact that asteroids are small rocks floating in space offers several advantages, but also some disadvantages. Their extremely low gravity, because of their small size, is one of the greatest advantages. This low gravity would make construction of huge structures much easier and would reduce the costs of landing and launching rockets in comparison to the Moon's or Mars's higher gravity wells.
The gravity is so low on these little objects that it's more akin to going and docking with the International Space Station or rendezvousing with something like the Hubble Space Telescope. So you're not going to be walking on these objects, you're going to be floating near them. And it makes, in some aspects, it makes that portion of doing a mission to one of these objects a lot easier.
Another pro would be the large number of possible sites because of their numbers, with over 300,000 asteroids identified to date, as well as their variety in chemical composition, with carbon-rich, metallic, and stony asteroids.
There are metallic elements and water in the surfaces of those little asteroids that are great resources for us out there in space once we have a thriving working economy out there. If you want to make rocket fuel to power your spacecraft that are moving around the inner solar system, it's a lot easier to make that fuel from the material on a little object with very little gravity than to have to haul it off the Earth all the time and lift it out of this deep gravity well. So the asteroids have great benefits for us, exploration and science and resources. I think they're wonderful destinations.
However, to make this future mining industry a reality, we need to solve several challenges such as asteroids' low gravity and zero atmosphere, which make them vulnerable to cosmic radiation and to the impact of small objects.
We've never actually had any experience in human spaceflight of working in a very low gravity environment that's very geologically dirty. Unlike on the Moon, where if you stir up dirt, it very rapidly settles again, on a little asteroid, if you stir up the dirt in that environment, it's going to stay around you in orbit around that asteroid for the entire rest of the duration of your mission. It's going to contaminate your spacecraft, it's going to contaminate your suit, it's going to make the visibility environment difficult. So there are challenges like that. Combining the challenges of a zero gravity EVA, a spacewalk, with the dirty environment of something like the Moon is something we have no experience with. And that's going to be, I think, one of the biggest challenges in human crews working around these little objects.
In a not-so-distant future, asteroids may become our new industrial target, a place to mine to benefit from their resources, used not just on Earth, but especially in space.
We can build the infrastructure that moves industry in space, not in 20 or 50 or 100 years, but starting in 3 or 4 or 5 years. And we can be harvesting rocket propellant in less than 10 years and building the transcontinental railroad to the solar system.
They might also become pit stops on the long journeys to Mars, and who knows, to our new home as well.
That is where the value of asteroids really lie, as they become gas stations or pit stops or stepping stones in our process to explore further and further into the solar system.
We are about to go one step further in the conquest of space, as the asteroids could soon become our next frontier. After more than 2 years of travel, on December 3, 2018, the Osiris Rex probe finally reached its target, the asteroid Bennu.
Asteroid Bennu is a carbonaceous type asteroid, so that means it's predominantly made of carbon, much like we are here on Earth and what primarily Earth is made up of.
The culmination of this NASA mission's adventure will occur when the spacecraft sampling arm touches the surface of Bennu, collects some asteroidal material, and brings that sample back to Earth. This tiny sample will allow us to answer big questions like where we come from and what is our destiny. Bennu hides secrets about the history of the Sun and planets, as well as the origin of life, since it, like all asteroids, is the leftover debris from the solar system's formation process.
Asteroid Bennu is an interesting asteroid to study for a number of reasons. It's the first carbonaceous type asteroid that we've gone out to collect the sample from, and carbon type asteroids are the type of asteroids that could have brought life to Earth in its early days of formation.
Bennu is just one of the hundreds of thousands of asteroids that float in the space in our solar system. These tiny rocky worlds are irregularly shaped, though a few are nearly spherical, and they are often pitted or cratered.
So most asteroids are located in a belt between Mars and Jupiter that we call the asteroid belt.
However, there are more asteroids in other locations. The so-called Trojans are asteroids that share an orbit with a larger planet, but do not collide with it.
Trojans are just objects that happen to be at what we call a Lagrange point of a planet. The Lagrange point is 60 degrees before or after. And the way to think about it is that if you take a planet and the sun, the gravitational force of an object at exactly 60 degrees between those two objects, plus the centrifugal force of rotation, all cancel out. So if you put something at that 60-degree point, it'll stay there forever. And so these Trojans, therefore, are leftovers of the formation of the planets. And that's what makes them so interesting, is that they're an ancient population that shared an orbit with Jupiter.
The main population of Trojan asteroids are the Jupiter Trojans, which is thought to have as many asteroids as those in the asteroid belt. There are also Mars and Neptune Trojans. However, they are not as numerous as the Jupiter ones. The other major population of asteroids is the near-Earth asteroids.
There's also near-Earth asteroids, and these are asteroids that cross the orbit of Earth. So they're ones that could potentially hit Earth.
The near-Earth asteroid population is about 1,000 times less populous than the asteroid belt. The main asteroid belt has about 1 million objects larger than about 1 kilometer. And the near-Earth object population has about 1,000 objects larger than 1 kilometer.
However, not all asteroids that float around our solar system belong to one of these populations, near-Earth asteroids or Trojans, or are trapped in the main asteroid belt. There are rare exceptions. On October 18, 2017, an unexpected discovery shocked the international scientific community. Astronomers discovered that a very weird asteroid passed by the Earth.
This asteroid seems to be at least 3 times as long as it is wide. It is possibly as much as maybe 8, 9, or 10 times as long as it is wide. This is something we have yet to see in our solar system, and how it gets produced is something we're not sure how to do this at this point.
The object was initially thought to come from the Oort cloud, a region far outside the solar system, which can have extreme orbits that take them careening through the inner solar system at speeds exceeding 37 miles per second. This strange celestial body was so significant because it moved at the astounding speed of 54 miles a second, too high to have come from our solar system. The conclusion was clear. It had to have originated from another solar system, making it the first ever discovery of an interstellar object. They named it Oumuamua. which means something like first distant messenger in Hawaiian.
Oumuamua is the first interstellar asteroid we've ever seen. So this is an asteroid that came from another solar system. And it came and it passed through our solar system and is on its way out of our solar system. And that's really amazing because we live at a unique time when our telescopes have gotten better and we're scanning the skies regularly and we're able to detect this first interstellar asteroid. It is likely that other objects have passed through our solar system and we just never were aware of it.
Perhaps it is a messenger from another star system, but what can it really tell us about where it came from? Since it was moving so quickly, the time available to study it was extremely short. As a result, soon after its discovery on October 24th, a wild race began between astronomers from all around the globe to obtain telescope data and unveil its secrets. We were able to analyze Oumuamua's chemical composition using photometric colors and spectra that revealed that it has a reddish color and might have come from the inner part of its original star system. However, the great mystery surrounding this interstellar object was its extraordinary speed of 54 miles per second, much higher than any other object from our solar system.
That object had anomalously large non-gravitational forces. So that was a little unusual. With comets, when you see non-gravitational forces, you tend to see dust produced because the gas is escaping and it lifts the dust off the surface. The interesting thing about this object is we didn't see any dust. So the question is, how can you get gas escaping and not produce dust? And that's telling us something that this object is unusual, at least compared to objects that are made in our solar system. And that's sort of a mystery.
Although we don't know Oumuamua's exact composition yet, we know the composition of asteroids that have been observed and studied for decades. Most asteroids fall into the following three categories: C-type, S-type, and M-type. C-type, or carbonaceous asteroids, also known as chondrite asteroids, are the most common. Their composition is believed to be similar to that of the Sun, although they lack hydrogen, helium, and other volatile compounds. They are dark in appearance, and they are among the most ancient objects in the solar system. S-types, or stony asteroids, are made up of silicate materials and nickel iron. They account for approximately 17% of all asteroids, and they are the second most common.
One is one we call S-type. These are often ones that were referred to as more stony type objects, and we think are very similar to a type of meteorite that's very common that lands on the Earth called ordinary chondrites.
M-type asteroids are metallic and much brighter than C-type asteroids. They are made of nickel, iron, iridium, platinum, gold, or other precious metals, either pure or mixed with different amounts of stone.
M-type asteroids are very unusual. Some of them may actually be metal. They may actually be produced in the interiors of asteroids. The core material has managed to escape the asteroid, probably in some gigantic collision. Other M-types, though, may be different compositions altogether, and there's still a great uncertainty about exactly what all of the M-type asteroids are.
If we want to study the composition of an asteroid, one of the best ways to do so is to analyze meteorites at an automated mineralogy lab, since many of them come from asteroids. The team at the Mineralogy Lab of the Geology and Geological Engineering Department at the Colorado School of Mines can examine the compounds of any meteorite sample with extreme precision.
All meteorites are fragments of rocky or metallic matter that's been transported from objects out in the solar system, and they've landed on the Earth's surface. And we can collect them and study them in the laboratory and work out their chemical composition, which minerals they contain, and therefore we can extrapolate the resource potential of particular bodies that exist elsewhere in the solar system.
Our automated mineralogy system is SEM-based, so we're using a scanning electron microscope to basically scan our sample. We have to prepare the sample. It is really important that our samples have a perfectly flat surface. So we have to polish our samples down to 1 micron. So the surface is perfectly even, so when we have the beam interact with the sample, we don't have other interaction features that will change the result of our interaction. We have our electron beam interact with the sample, and then we investigate basically the interaction product we get from the beam interacting with the sample. The result from this interaction we compare with the lookup table, where we have definitions for all minerals and phases that are of interest to us. And then our software program, the automated mineralogy software, will produce a false color map based on the definitions written and based on how it compares the analytical data with our lookup table.
Therefore, we can determine if the sample has more or less iron, nickel, platinum, or more or less of any other mineral. All asteroids, no matter their composition, are rocky remnants left over from the early formation of our solar system about 4.6 billion years ago. So they offer us clues to unveil the most hidden secrets of our most remote past. We've been exploring and studying asteroids for decades to understand what happened before us, before life on Earth, and even before Earth itself. Asteroids, considered floating fossils, can help us trace the solar system's evolution from a primordial disk of dust and grains. Asteroids can help us understand how the planets were formed and the origin of life on Earth, since there are theories that claim that the massive impact of asteroids was mainly responsible for delivering elements of life to primitive Earth. Asteroids are not just remnants of the remote past. They are also real hazards to Earth. Some pass close by Earth and could hit our planet one day, as occurred in the past when one ended the reign of the dinosaurs.
There was a 10-kilometer asteroid 60 million years ago that hit Earth. That's one of the current stories about the dinosaur ending event. Presumably we could have another asteroid impact like that at some point in time in the future, although right now it's not showing up as likely. We haven't found it yet.
A few years ago we saw an object the size of a large office building impact over Chelyabinsk, Russia. Very much smaller scale event, but still, in some ways, devastating for that particular city.
Scientists continuously monitor Earth-crossing asteroids, whose paths intersect Earth's orbit, and near-Earth asteroids that approach Earth's orbital distance to within about 28 million miles and may pose an impact danger.
The question is what to do about this. So right now, NASA has several ground-based surveys that use telescopes to scan the sky and look for threatening asteroids. They're trying to find all the asteroids that might present a threat to the Earth in the future. So far we've had some success with this, where we think we've found all of the 1-kilometer asteroids and larger bodies that can hit the Earth. But as we go to smaller worlds, we go to, let's say, worlds that are half a kilometer or 100 meters or so, these objects are still threatening. We're still working to find some of these bodies.
Bennu the target of the Osiris Rex mission, is one of the most potentially hazardous asteroids to Earth that is currently known, even though its odds of colliding with Earth are still relatively small.
NASA hasn't been able to control or change the trajectory of any asteroids yet. We are really at the beginning of understanding the types of asteroids that could impact Earth and how we might redirect them, which is one of the goals of the Osiris Rex mission, is to understand how the asteroid Bennu actually orbits and what we might do in the future to redirect it.
In fact, there is a NASA mission, the DART mission, that will test a technique for defending the planet from a future hypothetical asteroid impact, the main goal of which is to attempt to change the trajectory of an asteroid. Currently, there is no coordinated international plan to act in the event a potential hazardous asteroid is detected. Nevertheless, there are several non-governmental organizations that are focused on this issue. One of the most active is the B612 Foundation, which works toward protecting the Earth from asteroid impacts and informing and forwarding worldwide decision-making on planetary defense issues.
There are a number of groups worldwide that are concerned with asteroid detection and defense, and one of them is the B612 Foundation.
The B612 Foundation works to make interpretation of asteroid data open and accessible, and serves as an informed source for an international community of policymakers and scientists who can best help to achieve these goals. We haven't had any of these extinction-level events in recent history, but there might be one in the future if we don't do something about it. Some of Earth's largest craters, which are millions of years old, are large enough to hold a big city or even a small country. One of the most stunning craters that was recently discovered was in a remote area of northwest Greenland, buried under 0.6 miles of ice. It's 1,000 feet deep and 19 miles in diameter, which is bigger than Paris. That crater formed less than 3 million years ago, when a meteorite more than half a mile wide smashed into that area. The devastation that an impact like that could cause today would be catastrophic. Over the last decade, governments have started to gain awareness of this threat and have begun to make progress on the planetary defense front. With the ground-based U.S. National Science Foundation's Large Synoptic Survey Telescope, the LSST, 5 years from entering service, and with the selection of the Space Telescope NEOCAM as a finalist in the NASA Discovery Mission Program, scientists will be able to track 90% of near-Earth asteroids larger than 460 feet in about a decade.
We have to do something, or one day we will not be around anymore to ponder the asteroid problem. The asteroid problem will have done away with us.
Asteroids are among the oldest celestial bodies in the solar system. As floating fossils that witnessed Earth's primordial stages, they convey key information about the origin of life, as they are believed to have delivered the elements of life to Earth during its early stages.
Asteroids are fascinating celestial bodies that are somehow misunderstood. The asteroids hold the answers to many of the secrets that can help us to understand our own planet.
In addition to asteroids, comets and other small bodies offer clues that can help us understand Earth. Comets are very similar to asteroids. Both are remnants of the very distant past, like flying fossils from the origin of the solar system. However, while asteroids consist of metals and rocky material, comets are made up of ice, dust, rocky materials, and organic compounds.
A comet is an object that shows activity, and asteroids generally don't, although there are rare occasions of asteroids that show activity as well. The comets typically have a very eccentric orbit. So when it comes closer to the sunlight warms the gases and ices in the comet and creates a gas and dust tail.
2 missions targeting comets have helped us to unveil some of their secrets. NASA's Deep Impact mission and ESA's Rosetta mission, one of the most important missions led by the European Space Agency. In 2005, some of our ideas about the formation of comets and their role in delivering the elements of life to Earth changed thanks to NASA's Deep Impact mission, which was a pioneer in the study of these mysterious and beautiful celestial bodies. The probe reached the comet Tempel 1 on July 3, 2005, and the following day it successfully released an impactor on the surface of the comet, which generated a brilliant flash of light, later discovered to be ice and dust debris ejecting from the fresh impact crater. The Deep Impact mission was the first attempt to peer beneath the surface of a comet. It revealed a number of new findings about comets and their composition, including evidence of water ice and organic materials.
The Deep Impact mission was a wonderful example of the kinds of technology that we want to have available to us in the future for deflecting the trajectory of a potentially hazardous object. Deep Impact was purposely targeted to impact the nucleus of Comet Tempel 1, not for the purpose of pushing it off course, but for the purpose of studying what the subsurface properties of that comet are like. The side benefit, of course, was this is the first time we'd ever done something like this, purposely targeting a spacecraft to slam into a small object in the near-Earth environment. And so it was a great accidental practice, if you will. It was an unintentional practice of the kinetic impact method of deflecting asteroids.
However, we had to wait almost a decade until the next mission to a comet to discover more about these mysterious celestial bodies. It was ESA's Rosetta mission, a spacecraft sent to the 67P Churyumov-Gerasimenko comet by the European Space Agency, that gave us new evidences about comets. On November 12, 2014, an unbelievable milestone was reached when it successfully deployed its Philae probe on the comet's surface. The first time in history that such an extraordinary feat was achieved. Rosetta gathered significant data on the comet. It revealed that it had a remarkable array of surface features and many processes which contributed to its activity, painting a complex picture of its evolution.
Coming with the Rosetta mission, one of the strong motivation was whether or not comets played a role in delivering water to the Earth or potentially even organic compounds. I believe some of the outcomes from the Rosetta mission are now clearly showing that the comet didn't really play much of a role in delivering water to the Earth. We can look at isotopes of hydrogen, for instance, and deuterium on the comet, and they have distinct properties to what we find on water on Earth. And so there doesn't seem to be much room for delivery of water from comets. So that is an important aspect. Regarding the organic material, this is still an ongoing debate. Clearly, comets contain lots of organics, and so in principle, there is an opportunity to deliver organic material to the surface of the Earth, but it's totally unclear whether or not they actually played any significant role in the, let's say, formation of complex organics on Earth that eventually led to the formation of life.
The main shocking conclusion after all the data gathered was analyzed was that comets didn't bring water to Earth. Regarding asteroids, there are theories that suggest that they might have planted the ingredients for life on Earth. The key point would be to know how much water they have, which would be considered evidence of how they helped plant the seeds of life on Earth. There are two ongoing missions that may provide an answer to this question. The Japanese Hayabusa 2 mission to the asteroid Ryugu, and NASA's Osiris Rex mission to the asteroid Bennu. Both missions will collect asteroidal materials and bring them back to Earth for in-depth analysis.
The Osiris Rex mission to asteroid Bennu is a sample return mission to detect amino acids on an asteroid and bring back a pristine sample to Earth for study here.
We will learn a lot from comparing the two asteroids, Bennu and Ryugu, and understand the similarities and differences between their samples. The first one to be launched was JAXA's Hayabusa 2 mission, a mission of the Japanese Aerospace Exploration Agency that left Earth in December 2014.
Hayabusa 2 mission is visiting an asteroid called Ryugu. It's about 1 kilometer across. It also seems to be a primitive carbonaceous chondrite, but the interesting question is, did it come from a different parent than, let's say, Bennu? It's possible that both of these asteroids came from very different parent bodies originally in the asteroid belt, but it's also possible they came from the same parent body. In the process, we're going to learn about the nature of very large asteroids that are primitive in the asteroid belt.
It successfully reached Ryugu on June 27, 2018. It landed 3 hopping rovers on the surface of the asteroid. Some of these rovers have already sent home stunning images. However, the climax of the mission came on February 22, 2019. That day, the spacecraft was able to make the most complicated maneuver, the first touchdown. The probe was able to grab a tiny sample of dirt off the surface of the asteroid. It was the second time that humanity has ever achieved such a feat. These are the actual images of the historic moment of the first touchdown. Hayabusa 2 is hoping to bring back to Earth between 10 to 100 milligrams of material for in-depth analysis. The goal is to clarify the origin of life by analyzing samples acquired from a primordial celestial body, such as the C-type asteroid, to study organic matter and water in the solar system, and how they coexist while affecting each other. The other asteroid sampling mission that is now underway is NASA's Osiris Rex mission. On December 3, 2018, after a 1.2 billion mile journey, it reached its asteroid target, Bennu, and started to orbit. It is scheduled to bring back a sample of this mysterious celestial body to Earth in a sample return capsule in 2023.
The Osiris Rex mission launched in September of 2016, and it's a 7-year mission to go out to the asteroid. So we're going to reach the asteroid in 2018 and perform science studies of it through 2019 and 2020. And then in 2021, we will begin our return back to Earth.
The Osiris Rex mission will answer some key questions about the origin of the solar system, since as an asteroid, Bennu is a flying fossil from our solar system's most remote past, and about the origin of life on Earth, since as a carbonaceous asteroid, it may contain molecular precursors to the origin of life and Earth's oceans.
One of the reasons why we want to find out whether or not there are amino acids on Bennu is because we're not exactly certain how the building blocks of life got on Earth in the first place. One of the theories is that asteroids may have impacted Earth while it was in its early formations, and if those asteroids had amino acids on it, then it would have seeded life here on Earth.
Osiris Rex will determine Bennu's physical and chemical properties, which will be critical information to have in the event of an impact mitigation mission. It is scheduled to touch down on the asteroid's surface with the touch-and-go sample acquisition mechanism, or TAGSAM, that consists of a robotic arm with an attached sampler head.
We use the TAGSAM arm, which is kind of like a really expensive vacuum cleaner, which reaches out and touches the surface of Bennu from about 6 feet away and uses nitrogen to stir up the dust and the regolith that's on the surface of the asteroid. And that gets collected inside of a round collection plate, which we then store on side of the spacecraft and bring back to Earth.
From the most distant asteroids orbiting beyond Jupiter to near-Earth objects, each space rock contains clues to trace the epic events that shaped our solar system as we know it today. By studying these small bodies, we can learn more about how they accreted to form larger planets and about the time period when they massively impacted primitive Earth's surface. Everything started with a primordial disk comprised of grains of dust, which were tiny particles of rock, metal, and ice swirling around our primitive sun. Asteroids can help us investigate how the planets were formed from the progressive accumulation of smaller objects.
Well, an asteroid is sort of a leftover piece of the original building blocks which made the planets. Okay, originally we think our solar system was mainly made up of gas and dust. And slowly the dust began to form in larger and larger objects and became objects very similar to the asteroids we have today. Continued to grow, and ultimately they became into planets, they became into large objects in general. But some of the smaller objects that didn't manage to get into the planets became sort of the leftovers, and they're what we know today as asteroids. So these bodies have changed very little since the earliest times in solar system history, about 4.5 billion years ago.
Asteroids can help us investigate how the planets were formed from the progressive accumulation of smaller objects. Two of the most peculiar celestial bodies that may help us understand how the planets were formed are Vesta and Ceres. They are the largest bodies in the main asteroid belt, two protoplanets that never grew enough to become planets. NASA's Dawn spacecraft, which recently ended its mission, orbited both and definitely demonstrated that they are quite different from regular asteroids.
The Dawn mission is a NASA mission that was taught to investigate with great details the main objects in the asteroid belt. The targets were the asteroid Vesta and the dwarf planet Ceres, which are the most massive object in the asteroid belt in between the orbit of Jupiter and Mars. The name of the mission tells already what the mission is about. Dawn means, really try to understand the origin of the solar system, how the solar system was formed. And these objects, the targets of the missions, were considered and are still considered to be objects that formed very early on in the solar systems.
We almost call these dwarf planets. One is called Ceres, which is over 900 kilometers across. The second one is called Vesta, which is over 500 kilometers across. These two asteroids have very different compositions and a very different nature.
On November 1st, 2018, Dawn ended its mission. Currently, it's in orbit around Ceres, where it will remain for decades. Dawn found that while many asteroids are loose collections of rubble, the interiors of Vesta and Ceres are layered with the densest materials at their cores.
The asteroid Vesta seems to almost be like a little version of a planet that formed in the inner solar system. We believe it got so hot that it melted at one point, forming a core. It actually has material on the surface that makes it look like it's actually gone through volcanism, where basaltic material has come out and flowed across the surface of the rest. We actually believe we have some kinds of meteorites that actually came from this asteroid Vesta. And so we've been investigating that world to try to see the differences between what we could see from a spacecraft mission and what we can see from the samples that arrived on the Earth.
It's fascinating to think that we have a chance to directly study a piece of Vesta here on Earth. Thanks to some meteorite samples, the team of the Mineralogy Lab of the Geology and Geological Engineering Department at the Colorado School of Mines can investigate the main compounds of the surface of the protoplanet.
This one is a howardite, so it's an impact pressure. And these are little bits of rock on the surface of Vesta that were smashed up during other asteroid impacts. And these bits of rocks were thrown about the surface, accreted together. They were fused together by the regolith, and then a later meteorite impact has thrown this piece off Vesta's surface and it's impacted the Earth. This sample here is a diagenite. So this is like a gabbro that we would find on Earth, and this forms at some level within the crust, and it's an igneous rock. So it crystallized from a magma at some point in time. And if we can study the chemical compositions and the proportions of the minerals that exist here,
the results from the analysis of these samples will give us their precise composition.
In the samples we have for this meteorite, you can find pyroxene and anorthite, you can find some apatite, some spinel, some quartz of course, and those types of minerals. So the brighter the spot, the more iron content there is. So you see these gray areas have some iron content, but the most iron content is in these white spots, pixels here. So there's a good majority of this meteorite that actually has iron, but there's more concentrated spots throughout it.
The Dawn mission also studied Ceres, the biggest object in the main asteroid belt, revealing that it was an icy ocean world where water and ammonia reacted with silicate rocks.
Ceres, instead, is an entirely different object. It has much higher content of volatiles, potentially also including some water. On Ceres, we find, for instance, minerals that are the results of what we call aqueous alteration. That simply means when you have rock interacting with water, you can form deposits, for instance, like carbonates. These are common things that we find on Earth. Ceres and Vesta are considered remnants from the early solar system. By studying these objects, we can really try to understand the details of the early formation of the solar system. This object, along with many other asteroids that are found between Mars and Jupiter, didn't have an opportunity to grow to larger sizes, like a full-blown planet like Mars or the Earth. And there are several reasons why this happened. We think the main reason is because Jupiter, which was a massive planet, is not far from this region of the solar system. Jupiter has enough perturbation to those little planetesimal, small planets that were trying to accrete in order to form a much larger object.
Thanks to several pioneering missions to certain asteroids, we have been able to learn more about the origin of our solar system, about the role asteroids played as the building blocks of planets and in delivering the elements of life. Nonetheless, some unsolved mysteries remain. One of these mysteries is what is at the core of large planets. Although we can indirectly study the deep interiors of planets for clues about their origins, it's impossible to drill down into the core of any sizable object in space, including Earth. Nevertheless, a rare object called Psyche may offer the opportunity to explore a planet-like body's core without any digging. The asteroid Psyche, appears to be the exposed iron-nickel core of a protoplanet, a small world that formed early in our solar system's history but never reached planetary size. Like Vesta and Ceres, Psyche's path to planethood was disrupted. There's an upcoming mission to this unique and strange asteroid that will help tell the story of planet formation by conducting an in-depth study of this metal object. NASA's Psyche mission. The mission is scheduled to launch in 2022 and will reach its target after a 3.5-year journey in 2026. It will help us to understand a previously unexplored building block of planet formation, iron cores.
We've never actually had a chance to visit a world that's made out of iron, which may be a metal world. We think the way you would get metal worlds is possibly they are the cores that have been extracted from a larger, probably asteroid, or maybe even a small mini planet that was blown apart by some gigantic collision very long ago. So this is our opportunity to see what cores of worlds may be like. But there's also this interesting question about what should geology be like on an iron world?
The history of the solar system is written in cataclysmic events that began in the early stages of the primordial nebula, that became the primordial disk of grains of dust. Giant collisions between bodies were central to its evolution. The position of the planets has shifted due to huge gravitational interactions, and these planet migrations are thought to have played a key role in the solar system's early evolution. The Trojans, as ancient remnants of that remote past that are trapped in the orbit of some planets, could help us understand what happened. In fact, Jupiter's Trojans could give us clues about what happened the last time Jupiter moved and about what role it played in the organization of the planets of the solar system.
Lucy is going to visit 6 what we call Trojan asteroids, which are these asteroids that lead or follow Jupiter in its orbit. One of the surprising things about the Trojan asteroids is that although they occupy a very small region of space, just this little region near Jupiter's orbit, they're physically very different from one another. Is that they formed at very different locations in the disk, and the gravitational evolution of the planets led to a large number of objects from that outer region being trapped in this little region.
NASA's upcoming Lucy mission, scheduled to launch in October 2021, will explore Trojans for the first time ever.
We're going to be visiting objects in both swarms. The whole idea of this is to understand the diversity of these Trojan asteroids, what makes them different, because that's going to be a key to understanding how our solar system formed. This is named after the discovery of the Lucy fossil. The Lucy mission is named after the hominid fossil, the Australopithecus fossil, Lucy, that was discovered in the 1970s. Just like the Lucy fossil revolutionized our understanding of hominid development, the Lucy mission will revolutionize our understanding of solar system formation and evolution.
Lucy's discoveries will give us new insights into the origins of our Earth and ourselves. Asteroids don't just make it possible for us to learn about the evolution of the solar system or the formation of the planets. They also offer us almost unlimited resources. They contain natural resources such as water, organics, and precious metals. In the near future, these asteroids may fuel the exploration of the solar system by robotic and manned spacecraft. They could become useful pit stops or stepping stones en route to more distant destinations like Mars or beyond. There are no gas stations in space yet, But scientists and engineers are already starting to think about how asteroids could one day serve as refueling stations for spacecraft on the way to faraway space destinations. These small worlds might also help astronauts restock their supplies of water or other materials. Asteroids are not just small celestial objects, but extremely small worlds that can help us understand our own world, Earth, as well as the solar system. They can offer us clues about its origin, its evolution, the formation of the planets, and even about the origin of life. Current technology allows us to dream of a not-so-distant future where asteroids will be pit stops for deep space exploration, as well as sources for mining metals, minerals, and propellant to be used in space and maybe on Earth. This is only the beginning of the adventure. The exploration of asteroids has just begun.
Life, an unbelievably perfect combination of elements able to create living matter. Possibly the biggest mystery of nature. A combination of matter that shows certain attributes that include responsiveness, growth, metabolism, energy transformation, and reproduction.
We don't yet know exactly what life is. We don't have a working definition. Probably my favorite definition is that life is some sort of chemical entity that is self-enclosed and is capable of Darwinian evolution by natural selection.
Some studies state that life may have begun in Earth as early as 4.1 billion years ago. That is still only slightly younger than Earth. A question arises immediately. Is life an exclusive phenomenon of Earth? There's no easy answer to this question. The chemistry of life begun shortly after the Big Bang, 13.8 billion years ago, during a habitable epoch when the universe was only 10 to 17 million years old. Life may have emerged independently at many places throughout the universe. Or life may have formed less frequently, then spread maybe by meteoroids or comets, between habitable planets in a process called panspermia. In any case, complex organic molecules may have formed in the protoplanetary disk of dust grains surrounding the Sun before the formation of Earth. According to these hypotheses, this process may occur outside Earth on several planets and moons of the solar system, and on planets of other stars, the so-called exoplanets. Since ancient times, humankind asked itself if we are alone in the universe, and if there is life beyond Earth. Those questions may not be easily answered. However, they have always fascinated us.
Astronomers have been interested in the question of life beyond Earth for a very long time. I mean, we can trace back through the ancient Greeks and Romans and Chinese writings speculation about life beyond Earth.
The main issue to search for life in outer space is to establish what are the life support conditions. A source of energy, such as from a nearby star, is needed to drive endothermic or energy-absorbing reactions. Raw materials, predominantly carbon, build and form organic molecules.
So the building blocks of life on Earth, and we know them, there are carbon, hydrogen, oxygen, nitrogen, and others. They are what we are looking on other planets to look for life as we know it.
These building blocks for life, at least as we understand it, are ubiquitous.
Also indispensable is the presence of a liquid or very dense gas as a solvent for biochemical reactions to occur quickly and stably. Liquid water, the life-sustaining universal solvent, at least on Earth, entails certain atmospheric composition and temperatures.
In order to have a habitable environment, you need three things. You need liquid water, and you need organic material, and you need energy. And there are a number of places in the solar system where all three of those things are thought to exist.
Now we already know the key conditions for supporting life. A question arises immediately. How many planets or moons in our solar system meet these conditions? Considering that one of the key prerequisites for extraterrestrial life is the existence of liquid water, there are 3 candidates in our solar system to have liquid water on its surface. The planet Mars, the Jovian moon, Europa, and the moon of Saturn, Enceladus. Besides Mars, Europa, and Enceladus, which might have liquid water on their surfaces, there is another candidate for supporting life in our solar system, Saturn's largest moon, Titan. Until 2004, Titan remained a great mystery to astronomers, as a dense, opaque haze prevented understanding of its surface. On 2004, the spacecraft Cassini reached Titan and released a small probe named Huygens. That would change everything. These are the images that the Huygens camera recorded as it descended through the haze. Titan's landscape is very similar to Earth's, with mountains, valleys, and plains. When the probe touched down on the surface, it revealed something no one expected. There were pebbles everywhere, similar to the rocks of riverbeds on Earth.
When you're looking at those pebbles, yes, they are rounded pebbles, and they have been rounded by torrents and rivers. But they are not rocks in the sense that we understand. They are actually water ice, so hard that it behaves like rock.
How were these rocks eroded? Is there liquid water on Titan's surface? At minus 180 degrees Celsius, water should be frozen solid. Cassini's radar had the answer. It showed us that Titan's surface has hundreds of lakes.
The big difference, though, is that they are not made of liquid water. They are made of liquid methane.
These 2 hydrocarbons on Earth are volatile gases, but with Titan's chilly temperatures, they are liquid.
The atmosphere of Titan has methane and ethane and other organic materials that provide a very different kind of chemistry, but a kind of chemistry that is reminiscent of what Earth very possibly looked like before life was abundant.
All these worlds are very far away from the heat of the sun, so they are extremely cold, and some of them are exposed to very high levels of radiation, as they have very thin atmospheres. Therefore, their environments are quite hostile to life. However, life might have found its way.
We also now know about extremophiles, forms of life that live in environmental conditions that when I was a student, I was told, impossible. Can't have any life there. It's too hot, it's too cold, it's too acidic, it's too basic, too much pressure, too much radiation. They have evolved to thrive in those conditions. So this whole new field of study of extremophiles, it's a game changer. It changes what we think about the possibility for life somewhere else.
Extremophiles such as bacteria that live in high temperature, toxic, deep-sea hydrothermal volcanic vents on Earth offer insight into life that could have developed on other planets that mostly share such extreme, inhospitable environments, which also can include freezing temperatures and minimal sun exposure.
This gave us such a different view of actually what was necessary for life to survive. And all of a sudden, the solar system totally exploded. The horizon of what we call habitability and habitable environment completely expanded in ways that we could not have expected at all.
The chances of finding life on any of these remote worlds in the solar system are now much higher. Finding it is simply a matter of time. Of all 160 or so planets and moons in the solar system, Mars has so far received the most interest from astrobiologists. There are many signs that show that very early in its history, Mars was much like Earth, with large areas of liquid water, a thick atmosphere, ample sources of energy for life, and a good inventory of organic molecules.
In fact, what I like to say when I compare the two planets is that you don't have to invent words to describe Mars. You have mountains, you have canyons, you have polar caps, you have dunes.
There is evidence that Mars had a warmer and wetter past. Dried up riverbeds, vast canyons blasted out by epic floods, valleys carved by raging rivers, polar ice caps, volcanoes, and minerals that form in the presence of water have all been found.
There's a lot of evidence for liquid water earlier in the planet's history, much earlier, about 4 billion years ago, and perhaps some transient water in the time since 4 billion years ago.
But the evidence indicates that all that water disappeared from the surface billions of years ago as Mars cooled down and lost its atmosphere. Did life ever get a foothold on the planet?
As we are looking for evidence for ancient life on Mars, some people think that actually we already had some evidence of that life landing on our own planet. And the best example of that is the Allen Hill meteorites.
We had a piece of Mars here in the lab. We still have it. Allen Hills 84001, a rock that was chipped off Mars by an impact millions of years ago, wound around in space, landed on the Earth in the Antarctic ice sheets, and during the 1984 spring collection season, as that ice was melting and those black rocks were picked up in the melt pools, we realized by the gases that are included in that piece of rock that that's a piece of Mars. And we took it apart at microscopic scales. And we had a big scientific controversy because there were scientists that were claiming features in that rock could only have been produced by biology, and other scientists saying, nope, You can get that with geology.
The search for life on the red planet started decades ago. In 1976, a search for microbial life on the red planet was performed for the first time ever. 2 decades later, in 1997, the Pathfinder mission took a new step forward in this search for life adventure. It found magnesium, aluminum, iron, and phosphate in Martian rocks, which are all possible life-supporting materials. In 2008, the Phoenix spacecraft explored Mars' North Pole. After digging a few inches, it found a white material that evaporated several days later. The analysis of that material revealed it was water ice. Satellites scanned both polar caps and found that there was a lot of water ice under a layer of frozen carbon dioxide. If all that ice ever melted, a more than 80 feet deep ocean would cover the whole planet. The same satellites also discovered that there was ice buried everywhere beneath the desert plains. That was a shocking discovery. Mars had huge amounts of water ice everywhere. But could life exist in the buried ice itself? We now know that there are extremophile microorganisms able to live in similar environments in the dry valleys in the Antarctic, here on Earth.
Currently, Mars is very dry and very cold. It's like some regions in Antarctica today, and it's kind of like a very cold desert. So liquid water would not be stable. If you opened up a container of water, it would immediately evaporate because it's so dry.
Buried ice was found under a layer of dry dirt, as happens on Mars. At the point where the dirt met the ice, there was a thin film of liquid water where extremophiles thrived, just for a short time. These microorganisms remain frozen and dormant most of the year, and they only flourish for a few warm weeks during the summer.
Today, Marcus could still live at depth, some depth, favored by the presence of thin films of water or maybe more liquid water, because the deeper you go, the more the chance that water could be liquid.
During the Martian summer, it's common to reach 20 degrees Celsius at the equator, so the buried ice might melt and create similar conditions to those found in the Antarctic dry valleys.
Any microbes that might have been there, they're probably living within the rocks or under rock coatings. So that's one of the analog sites that my group's been investigating, is microbes that are living underneath the surface, because that might be viable for Mars as well.
A future mission could eventually prove whether this hypothesis is true or not. But there is another possibility, that liquid subsurface water exists on Mars. Mars' huge volcanoes, such as Olympus Mons, could contribute internal heat to sustain subsurface water. This would imply that hydrothermal vents could exist on Mars as well, and therefore it might be also possible that extremophiles, similar to the ones that thrive in the terrestrial hydrothermal vents, might also exist on Mars. However, this is quite unlikely. Everything would change if we were able to find liquid water on the surface. On September 2015, NASA's Mars Reconnaissance Orbiter made an incredible discovery. This spacecraft provided the strongest evidence yet that liquid water flows intermittently on present-day Mars.
It's not a pure transparent water. It's very briny water, very salty water, which allows it to remain stable for a little while at the surface because the pressure at the surface of Mars is very, very small.
What will really change our understanding of the Red Planet are the NASA and ECA missions, both part of the Mars exploration program. Since 2007, the main goal of space missions to Mars was not just to follow the water, whether in the form of ice or liquid water, but to explore its habitability, and above all, to seek signs of life.
The more we investigate Mars, we obtain more clues that the ancient history of Mars was certainly supportive of life, and then that final step of did life actually evolve, and then if it did, where did it evolve, and what clues are remaining today, because that was so long ago.
The ultimate aim of missions to Mars is to prepare for human exploration, a step that would really be a new milestone for mankind. The first step in this ambitious exploration program is the ExoMars program, a partnership between ESA and Russia's Federal Space Agency, Roscosmos, with the participation of NASA. Its primary scientific goal will be to search for possible biosignatures on Mars, past or present. ExoMars is a multi-spacecraft program. The first ExoMars mission, ExoMars 2016, is called the Trace Gas Orbiter, TGO. The goal of this orbiter is to study the Martian atmosphere for the presence of methane and other gases, gases that might be linked to some biological processes. The second mission in the ExoMars program is the 2018 ExoMars rover and landing platform. The ExoMars rover is a rover with a 2 meters core drill to sample various depths beneath the surface where liquid water may be found.
The drill was supposed to penetrate the first couple of meters within the sediments. This way is more probable maybe finding evidence of viable salts.
The third step of this enthralling Mars exploration program is the NASA mission, Mars 2020. The aim of the Mars 2020 rover is to study diverse rocks and soils to understand past habitable conditions on Mars and to seek signs of ancient microbial life. One of its functions is to monitor weather and dust in the Martian atmosphere and test the ability to extract oxygen from the red planet's carbon dioxide atmosphere to prepare for future human exploration. Any of these breakthrough missions might solve the enigma of whether there is past or present evidence of life on Mars. Much further away than Mars, there is another unique world that might harbor life. Our next destination in the search for life is one of the most fascinating Jovian moons, Europa. Europa is one of the 4 largest moons of Jupiter. It's slightly smaller than our moon, and its icy surface is minus 160 degrees Celsius. Virtually everything we know about Europa is thanks to NASA's unmanned space probe Galileo, which passed by Europa 12 times. These were the first images it captured. It is covered by a smooth layer of water ice. In fact, it has the smoothest surface of any known solid object in the solar system.
The surface of Europa is unique in the solar system. It's has very few craters, which tells us that the surface is being reprocessed frequently.
Some parts of its surface show blocks of ice that are separated, but seem to fit together like a puzzle. These icebergs could have been shifted by slushy or liquid water beneath.
These cracks probably may extend all the way down to the ocean, to the ocean, or at some point, so you could get some percolation of water.
This peculiar landscape is very similar to sea ice on Earth.
Galileo was able to detect that. All of those things together add up to our picture of how we now know that Europa has a liquid ocean under its surface.
In 1996, the Galileo spacecraft detected a magnetic field on the planet's surface, indicating that there must be some electrical conduction likely to derive from a salty ocean that could be 60 miles deep.
The studies and observations, measurements that have been made in the past decades seems to be converging pretty clearly with the presence of an ocean under the surface of the ice.
So there we have the first key ingredient for life, liquid water. How can water remain liquid at temperatures of minus 160 degrees Celsius? Some sort of mysterious internal heat must be melting the icy crust. Jupiter is the key. Tidal heating from friction due to Europa's eccentric orbit around Jupiter has been proposed.
The ice at the surface of Europa is being cracked. It's not completely sealed. You can see because of gravitational pull and pull, there is this tug of war as Europa is moving around Jupiter. You can imagine that all this friction is creating lots of energy, lots of heat, and then we have good reasons to think that there are hydrothermal system, which means that you have, water being heated by this process.
Volcanoes deep down may harbor hydrothermal vents that provide an energy source to heat and maintain liquid water. So we have two of the three conditions for life: a liquid, in this case liquid water, and a source of energy, that interior heat. We would just need some organic compound, and the chances of life arising would skyrocket. The Galileo spacecraft observed that Europa's ice contains carbon dioxide. When this carbon dioxide is strongly impacted by Jupiter's radiation, it can produce simple organic molecules such as formaldehyde that are steps towards life. The aforementioned tides on Europa could also mix life-supporting substances together in the ocean, but nothing has been proven yet. On 2013, NASA reported a surprising discovery on the icy crust of Europa. Some clay-like materials, specifically phyllosilicates, were detected.
Phyllosilicate just means phyllo, like layered silicate, and these are a fancy name for clays. And clays are a kind of mineral that forms in a lot of water. And on Earth, there are some theories that these clays were some of the original minerals that were present when life was evolving.
According to some hypotheses, the presence of these organic associated minerals may have been the result of a collision with an asteroid or comet. With liquid water, an energy source and the necessary chemical building blocks, perhaps delivered by comets or asteroids, Europa opens up the possibility that life could exist in places never imagined. "12,000 feet beneath the Arctic ice sheets, in complete darkness, there are hydrothermal vents that spew out superheated water with lots of toxic chemicals. scientists think vents like this could also exist on Europa's ocean floors.
We think that the potentially source of energy for an ocean Europa will be the volcanic activity.
We have recently discovered that clustered around the vents, there are extremophile microorganisms that cover miles of the Arctic seafloor. The discovery of life there really raises the possibility of life on Europa.
Probably Europa might be the best candidate for us to find extant life.
The challenge now is to prove that life has been able to thrive in such a bizarre environment. NASA and ESA have planned 2 different missions to Europa that will investigate its habitability in the next few years.
In 2015, NASA approved a new mission to go to Europa and investigate its environment, and particularly to look for habitability.
NASA's Europa Multiple Flyby mission is a spacecraft that will be launched in the 2020s. The spacecraft will be a highly capable, radiation-tolerant probe that will perform repeated close flybys of the icy moon.
We'll also be looking under the surface to learn more about the structure of the ice shell and the structure of the ocean underneath the shell, using radar and magnetic field detectors and other instruments.
The ESA is developing in parallel its own mission, the Jupiter Icy Moon Explorer, the so-called JUICE mission, that is planned for launch in 2022 and arrival at Jupiter in 2030. This spacecraft will spend at least 3 years making detailed observations, not just of Europa, but also of the giant gaseous planet Jupiter and 2 of its largest moons, Ganymede and Callisto. We will have to wait till the next decade to confirm whether or not there is life on Europa. Europa isn't the only intriguing place this far out in the solar system. Could similar conditions exist on other moons orbiting other planets, even further away from the Sun? Orbiting Saturn, there is a small, mysterious moon that is totally different from the rest of its more than 60 moons. This tiny icy moon, only 300 miles across, is Enceladus. In the last few years, this tiny moon has become the main goal for exobiology, as it has revealed some extraordinary conditions for harboring life.
Most of what we know about Enceladus is thanks to a mission called Cassini. It's a mission that it's been going on for many years. It's an orbiter that has been studying the entire Saturn system and its different moons, but it's been paying close attention to Enceladus.
The Cassini mission offered us a close-up of this remote world for the first time ever. These were the first images it took. The surface is white and glittering, and it is carved with fissures, crests, and cracks. At the South Pole, Cassini made a surprising discovery. It photographed some strange, large cracks, seen here in blue. 4 parallel fissures, scientists named the tiger stripes. They are 75 miles long and hundreds of feet deep. They are similar to fault lines on Earth. After several flybys, Cassini's thermal radar revealed something unexpected. The tiger stripes should be colder than the rest of the moon, as they were in the South Pole. However, they were radiating heat. The fissures were at minus 80 degrees Celsius, which was more than 120 degrees Celsius warmer than the rest of the moon.
It's definitely a place where we see evidence that something profound is happening in terms of potential for habitable environment.
But the most shocking finding was still to come. When Cassini was reoriented, it captured a shocking image. Vast jets of ice were erupting into space.
The camera was able to image plumes of water vapor and ice crystals coming off the south pole of Enceladus.
These actual images showed the plumes were ejecting ice particles hundreds of miles out from the tiger stripes.
Those materials are being ejected through fractures on the surface of the moon, which seem to be connecting the surface with the interior.
However, how this small moon can generate so much heat as to be able to maintain such geothermal activity? Scientists believe that Enceladus might have an internal energy source, like Europa. When it orbits the massive Saturn, friction from gravitational process causes it to heat up, melting ice in the moon's interior in the same way as on Europa. These jets were giant geysers of water that erupted from its icy surface, much like those in geological hotspots on Earth.
Cassini actually has a detector that can fly through the plume, pick up some of the particles and analyze them chemically. And when that detector did its work, it found that some of the particles are salty. And the only way to get salt incorporated into a particle is to have it evaporating directly off of liquid. So that was yet another hint that Enceladus has liquid under the surface from which these plumes are emanating.
But could it prove that under the icy crust of Enceladus existed a subsurface ocean, like on Europa?
We needed even more evidence. The next piece of evidence was from Cassini flying past Enceladus and just carefully analyzing its trajectory as it flew past Enceladus to directly measure how Enceladus's gravity was pulling on the spacecraft. And when that analysis was done, it found a density anomaly under the entire South Pole, indicating that you have a regional sea of water from which these plumes are emanating.
These jets might be connected to active hyperthermal vents at a subsurface water ocean floor, where the moon's ocean meets the underlying rock, a prime potential habitat for life. But there still wasn't anything that could prove life existed underneath that icy crust. The probe spectrometers detected something really exciting. They found in the jets the basic chemical building blocks of life.
So Enceladus is fascinating because, as far as we can tell, it contains the three basic ingredients for life: liquid water, nutrients, and organics.
But does this strange and alien world actually support life? The geysers could provide easy access for sampling the moon's subsurface ocean. And if there's microbial life in it, ice particles from the sea could contain the evidence astrobiologists need to identify them. There are 2 exploration missions proposed by NASA to Enceladus in the near future that would try to find evidence of life in the tiny icy moon. The first one is the Journey to Enceladus and Titan mission. This is an astrobiology mission concept to assess the habitability potential of Enceladus and Titan, moons of Saturn. The second mission, waiting for approval and financing, is the Life Investigation for Enceladus. This proposed mission would capture icy particles from Saturn's moon, Enceladus, and return them to Earth, where they could be studied in detail for signs of life, such as biomolecules.
It's relatively simple, technologically speaking, to send an orbiter to Enceladus that can capture those icy particles in the plume and analyze them in situ or bring them back to Earth for detailed analysis in the laboratory.
Unfortunately, none of these missions have been approved yet. So we will still have to wait to unveil whether or not there is life on this tiny, enthralling moon of Saturn. Close to Enceladus, there is the last of the great candidates for life in the solar system, Titan.
Titan is the largest moon of Saturn. It is one of the largest moons in the solar system, and it is also the only moon that is known to have a thick atmosphere.
Data from the Cassini-Huygens mission, which flew by Titan in 2004, demonstrated the existence of hydrocarbon lakes.
Titan is a fascinating world. It's the most alien place in the solar system, so to speak, because it, in fact, other than the Earth, is the only place we know of that has seas of liquid on its surface, but those seas are not made of water.
In these seas and lakes, there are no waves, as the liquid is liquid methane and ethane, which is much less dense than water liquid. These two hydrocarbons on Earth are volatile gases. But on Titan's minus 180 degrees Celsius temperature, they are liquid. Titan has a very similar landscape to Earth. There are seas, lakes, smoothed rocks on the riverbeds, mountains, valleys, canyons. But these mountains and pebbles are not made by any rock like on the Earth, but they are made of water ice, so frozen due to the minus 180 degrees Celsius temperature on Titan's chilly surface that it behaves like rock. Cassini's radar images showed that on Titan, liquid methane forms clouds, thunderstorms, and even falls as rain.
Methane in the atmosphere also plays a role similar to water in the atmosphere. On Earth, you have a water cycle. On Titan, methane plays a very similar role. It falls to the surface as rain or mist. We do see channels and rivers where methane is flowing across the surface and doing geological work like we would see water do on the surface of the Earth.
Liquid methane has a cycle very similar to Earth's water cycle. The question is, could it behave like water does on Earth, as a liquid that allows organic molecules to dissolve and interact? There is no easy answer to this. Titan's atmosphere also contains many organic gases, such as methane, ethane, and hydrocarbons, and possesses conditions that resemble those of early Earth 4 billion years ago that allowed life to develop.
In many ways, the atmosphere of Titan looks like a young Earth in the fridge, much colder. But prebiotic chemistry, the same processes are there. What we don't know is whether these prebiotic processes are turning into something that is biological in nature at the surface of Titan or in the subsurface.
However, liquid methane and ethane are much colder than liquid water by some 200 degrees Celsius, and biochemical reactions would occur at painstakingly slow rates. These compounds are also far less capable as solvents compared to water, and therefore much less life-inducing. Water is also missing from the picture due to freezing temperatures of minus 178 degrees Celsius. Several experiments have shown that with an atmosphere similar to that of Titan and the addition of UV radiation, complex molecules and polymer substances like tholins can be generated, substances that could be considered a sort of precursor to life.
What weirdo chemistry, physics, biology could be. People are trying to think in terms of what could be a biology based on methane. It's not the best, apparently, when it comes to provide a structure for biochemistry.
The conclusion is that Titan is a world rich in organic matter, with a methane cycle comparable in atmospheric and geological processes to Earth's water cycle, that is really likely to harbor life. In the last years, NASA and ESA have combined efforts to develop an unmanned space mission that could finally unveil all the Titan's mysteries. But none of them have been approved yet. One of the most exciting missions proposed to unveil the secrets of the methane and ethane lakes of Titan is NASA's Titan submarine. This submarine would explore the depths of the Kraken Mare, the largest known body of liquid on the surface. This mission would be designed to measure the organic constituents on Titan and would have performed the first nautical exploration of an extraterrestrial sea, analyze its nature, and possibly observe its shoreline. As the other proposed mission to Titan, this Titan submarine mission hasn't been given the green light yet.
There's lots of really fun options for exploring Titan, but NASA has not actually selected one of these options.
Therefore, to date, there are no confirmed space missions to Titan in the coming years. But everything could change if a shocking discovery is made in the near future. Whether or not any of these potential space missions finally reveal the existence of life on Mars, Europa, Enceladus, Titan is an unknown. But what we do know is that now we are much closer than ever to finally finding an answer to the question of whether there is life beyond Earth. "50 years ago, the era of robotic exploration of our solar system was just beginning. In July 1965, the Mariner 4 probe sent the first close-up images of Mars. Those blurred images showed that Mars did not have vegetation, much less canals crisscrossing the planet, as envisioned by earlier generations of astronomers. At that time, the most widespread opinion was that Mars was not just the red planet, but also the dead planet, with the chances for life of any kind being considered infinitesimal. Things have radically changed since 1965, thanks to the extraordinary advances of technology that have led us to use more and more sophisticated space probes to explore our neighbors in the solar system. The three vital factors, energy, liquids, and chemical building blocks, are more widespread than has ever been realized. Now it's not so unlikely to find life beyond the Earth in our solar system. We can't deny that such a huge discovery, even if it were just microbial life, would be really shocking for mankind, as it would imply the first step toward believing that we may not be totally alone in the universe. Then, the right conditions could also exist beyond the boundaries of our own solar system, in distant outer space. Is there life beyond Earth? Humankind has always asked itself this question, but no answer has yet been found. It appears that we are closer to solving this mystery. Recent discoveries have uncovered planets beyond our solar system that are believed to be similar in many ways to Earth.
If I got to ride on a spaceship to one planet that we found with Kepler, the one that I would go to is Kepler 186f. It's one of the smallest ones. It's at the right temperature that liquid water could exist on its surface.
Kepler 186f is the first validated Earth-sized planet to orbit a distant star in the habitable zone where liquid water might pool on the planet's surface. The discovery of Kepler 186f confirms that Earth-sized planets exist in the habitable zones of other stars and signals a significant step closer to finding a world similar to Earth. Kepler 186f orbits its star once every 130 days and receives 1/3 the energy that the Earth does from the Sun, placing it near the outer edge of the habitable zone. If you could stand on the surface of Kepler 186f, the brightness of its star at high noon would appear as bright as our Sun is about an hour before sunset on Earth.
Today, when we take a look at what we know about the origins of life on this planet, it leads us to think that the same things that happened here might well have happened elsewhere. And so life beyond this planet is quite plausible in terms of the science that we know today.
We now know there are 4 important candidates in our solar system to harbor life. Mars, Jupiter's moon Europa, and Saturn's moons Titan and Enceladus. On every of them, we can find all of the 3 key ingredients for life: organic compounds, a liquid, and an energy source.
There is water on Mars under the form of ice at the poles and under the surface, but it is also flowing from time to time at the surface during spring and summer.
Although there's no evidence of any form of life on Mars yet, scientists think it might be found soon. On Jupiter's moon Europa, 2 of those key ingredients can also be found.
We do know there is water on Europa. On the surface of Europa, we have an icy crust. This icy crust has been observed using Voyager spacecraft, but also the Galilean spacecraft in the 90s.
Under an eerie water ice crust, 10 to 30 kilometers thick, that covers this tiny moon, there's supposed to be a liquid ocean, which may be about 100 kilometers deep. The Saturn's moons Titan and Enceladus have become the search for life priority top spots in the recent years.
Titan is the only moon in the solar system that is known to have an atmosphere. It's also the only place in the solar system that has an atmosphere made primarily of nitrogen, except for the Earth. So Titan and Earth are closely linked in that way.
Titan is a fascinating world. It's the most alien place in the solar system, so to speak, because it, in fact, other than the Earth, is the only place we know of that has seas of liquid on its surface, but those seas are not made of water. They're made of liquid methane and liquid ethane.
Titan is the only place in the solar system outside Earth where there are stable bodies of surface liquid. But at minus 180 degrees Celsius, this liquid can't be water. We know there are lakes filled with super-chilled liquid methane and ethane. In recent years, Enceladus, a tiny moon orbiting Saturn, has become one of the main goals for exobiology. Enceladus is a small icy moon, quite similar to Europa, as it has a thick icy crust and an ocean beneath. We know there are vast jets of water ice erupting several miles into space.
Enceladus is one of the most interesting places in the solar system because of the presence of this activity, this geyser-like activity. If we have geyser-like activity, people expect to have water, liquid water.
Recently, in those jets, some of the basic chemical building blocks of life have been detected, so we can be sure that we have on Enceladus the trifecta to harbor life: liquid, organic compounds, and an energy source. But if life was able to emerge in any of those remote and harsh worlds, why couldn't it also arise on any other planet far beyond the boundaries of our solar system?
The second genesis within the same solar system implies that life, the origin of life, is a likely event. If it happens twice in the same solar system, it's likely happening everywhere in the universe.
If we were able to find life within our own solar system on another place, and furthermore, be able to say that it developed, independently, then you're saying within the same stellar system, you had life evolve twice. And the conclusion from that is that life forms very easily.
A generation ago, just the idea of a planet orbiting a distant star was still in the realm of science fiction. So, to think of the possibility of life on a planet like that was simply unimaginable. In fact, the first exoplanets weren't discovered till 1992. That very year, 2 super-Earth exoplanets were found around pulsar PSR 1257+12 at a remote distance of 2,300 light-years away. This announcement shocked the scientific community at that time, as it was the first multi-planet extrasolar system ever discovered. Could any of these super-Earth harbor life? Unfortunately, a pulsar is a very different kind of star from the Sun. In fact, it's a dead star, formed when some of the largest stars in the universe exploded as supernovae.
A pulsar, which is what's left after a star, a really massive star explodes, and you've got this thing which is one step away from being a black hole. While this was really exciting, it was hard to tell what it meant because pulsars are so much different from normal stars.
These may not seem at first to be good places to look for habitable planets. Supernovae are, frankly, quite apocalyptic events that would easily vaporize any ill-fated planets in orbit around the exploding star. That distant world would be bathed in a lethal cocktail of X-rays and charged particles emitted by a star so faint in visible light that it would scarcely cast a shadow on this world's surface. So the chances of life arising in such a weird and hostile environment would be remote. However, the real importance of this discovery was that for the first time ever, the existence of planetary systems beyond the limits of our solar system was confirmed. If we found 2 exoplanets out there, why couldn't there be many more? We had to wait 3 more years to find an exoplanet orbiting a Sun-like star, which was far more important because the conditions of such a planet would be potentially similar to any of the planets in the solar system. On October 6, 1995, was the announcement of the discovery of the first planet orbiting a Sun-like star in the journal Nature. That star was 51 Pegasi, a Sun-like star located 51 light-years away, and the exoplanet was a giant planet.
The first exoplanet found around a star like our own was called 51 Pegasi b. It's very unusual. It's a very large planet. It's bigger than Jupiter. It's more massive than Jupiter. And it's on a very short period orbit. It goes around its star. 1 year on this planet takes 4 days. It's a very short amount of time.
That discovery marked a turning point in the search for exoplanets. From that moment on, many new ones were found. Nevertheless, what radically revolutionized the search for exoplanets was the NASA Space Telescope Kepler.
Before Kepler was launched, there was hundreds of planets that we knew of in systems around other stars, and now we know of thousands. And that's why Kepler was so revolutionary.
The Kepler was a space telescope specifically designed to survey our region of the Milky Way galaxy to discover hundreds of Earth-size and smaller planets in or near the habitable zone of their respective stars and determine the fraction of the hundreds of billions of stars in our galaxy that might have such planets.
It works very simply. I mean, anybody can understand this. It's just staring at one spot on the sky all the time, never blinks. And it's looking at 150,000 stars. And it just monitors how bright they are, kind of like a camera light meter, really. And occasionally they'll see this star over here, for example. It'll get a little bit dimmer, a very fraction of a percent dimmer for a few hours, and then it'll get bright again. Well, that happens if a planet passes in front of that star.
We've gone from finding 100 planets to over 1,000 planets with Kepler, those that have been confirmed. And there's about 3,000 or 4,000 more which we have strong evidence for, but we wouldn't consider confirmed planets just yet.
Kepler is on the hunt for planets. Kepler has found literally thousands of planets or planetary candidates. It's a planet-finding machine.
In 2011, for the first time ever, Kepler provided scientists with a census of the Milky Way, so we could calculate how many stars in the Milky Way could have a planet like ours. Around 1 billion.
Maybe there are 1 million, maybe there are 1 billion, maybe there are 100 billion planets in the Milky Way galaxy that could support life, the kind of planets that earthly life could survive on. How many of them have cooked up their own life? And we don't know the answer to that, okay? Because that depends on how hard it is to get life started. Just because I give you all these, these worlds doesn't mean that life will get started. But on the other hand, those planets are all made out of the same stuff that Earth is. So again, unless something very unusual happened here and nowhere else, there's going to be biology all over the place.
Just 4 years after its launch, on April 2013, the Kepler team reported one of their first great triumphs, the discovery, for the first time ever, of 2 exoplanets very similar to the Earth, Kepler 62e and Kepler 62f. This discovery created great enthusiasm, as it implied the confirmation of Earth-like planets where life might be possible. Each of these planets have a radius 1.6 and 1.4 times of Earth, and orbits Kepler-62, an orange dwarf star, in its circumstellar habitable zone. A modeling study also concluded that Kepler-62e and Kepler-62f are likely covered mostly, perhaps completely, in water. Kepler-62e probably has a very cloudy sky and is warm and humid all the way to the polar regions. Kepler-62f would be cooler, but still potentially life-friendly. Unfortunately, they are at a huge distance of 1,200 light-years away in the constellation of Lyra. Thanks to the Kepler mission, we now know that there are tens of billions of planets orbiting stars just in our galaxy, the Milky Way, and we know there are billions of galaxies across the universe. So if in just one planetary system like ours, life arose on one planet, and there are at least 4 more candidates, the likelihood of finding a planet in outer space that could harbor life should be very high. But Kepler has discovered for us not only the existence of Earth-like planets, but also has provided us with amazing data about the universe, such as the confirmation of the existence of planets that orbit around not only 1, but 2 stars, like Kepler-16b. This planet was Kepler's first discovery of a planet that orbits 2 stars, what is known as a circumbinary planet.
So one of the most exciting discoveries from Kepler was that we were actually able to find planets around binary stars. And the first one that was found was Kepler 16b.
Kepler 16b is many people's favorite planet that was discovered with Kepler. It orbits around not one, but two stars at the same time. This was something which was predicted not to exist. Two stars setting at the same time was just a piece of science fiction. But the universe is stranger than what scientists can imagine, and it turns out that this sort of thing is true.
Since 1992, over 2,000 exoplanets have been discovered. Thanks to future Space Telescope missions planned for launch, the number of observed exoplanets is expected to increase greatly in the coming years. Despite having discovered just a tiny fraction of all of those billions of exoplanets that we think that exist, how could we know how many of them could harbor life? In astronomy and astrobiology, the region around a star where a planet with sufficient atmospheric pressure can maintain liquid water on its surface is known as the circumstellar habitable zone.
The habitable zone is a place, it's kind of a way of thinking about the right way to go look for planets like our own.
The Earth is obviously in the circumstellar habitable zone of our solar system. A potentially habitable planet implies a terrestrial planet with conditions roughly comparable to those of Earth, and thus potentially favorable to life.
There's a sweet spot, an area where it's not too hot and not too cold, and we call that the habitable zone, or some people call that the Goldilocks zone. If you've got a planet in that regime, and if it's small, if it's rocky enough, and it had water, that water would be in a liquid state, more than likely. So that would be a good place to go looking.
On November 2013, astronomers reported, based on Kepler space mission data, that there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of sun-like stars and red dwarfs just in our galaxy, the Milky Way, 11 billion of which may be orbiting sun-like stars. Those 11 billion exoplanets orbiting stars like our Sun really are a huge number of potential Earth-like worlds. However, now we know that stars very different from our Sun may be a good place to look for life. In May 2016, a team of astronomers announced, for the first time ever, the finding of 3 habitable planets orbiting a star completely different from ours, an ultra-cool dwarf star. It's the first planetary system found around a star like this. The star, named TRAPPIST-1, is just 40 light-years away and is much cooler and redder than the Sun, and barely larger than Jupiter. In fact, stars like this are very common in the Milky Way, and they are very long-lived. The 3 planets are very similar in size to the Earth and might have habitable regions on their surfaces. So the answer to what the best place in the universe is to find life nowadays has radically changed. To date, among all of the more than 1,000 confirmed exoplanets, there are around 50 that are in the circumstellar habitable zone of the star they orbit around. And therefore, they could be potentially considered Earth-like planets, which does not imply these distant worlds may harbor life. However, could life be possible outside those habitable zones? The discovery of hydrocarbon lakes on Saturn's moon Titan has begun to call into question the carbon chauvinism that underpins circumstellar habitable zone theory. Liquid water environments have been found to exist in the absence of atmospheric pressure and at temperatures outside the circumstellar habitable zone temperature range.
Just because a planet is outside the habitable zone doesn't mean that it couldn't have life.
For example, Saturn's moon Enceladus and Jupiter's Europa, both outside the habitable zone of our solar system, may hold large volumes of liquid water in subsurface oceans. If we are considering the possibility that life could arise in such harsh environments, which are not in the circumstellar habitable zone, that implies that we should look for exoplanets far beyond those zones. So the chances of finding an exoplanet with conditions to support life are much higher. We know that it's not an easy task to study and analyze the planets and moons of our own solar system, as they are millions of kilometers away from Earth. However, exoplanets are not just millions of kilometers away, but many light years away from Earth. How can astronomers manage to study exoplanets if they are trillions of kilometers away? There are several methods used by astronomers and astrobiologists to discover and to study these extremely distant, mysterious worlds. Before the launching of the Kepler mission in 2009, the most successful technique for detecting exoplanets was the Doppler spectroscopy, also known as the radial velocity method. The radial velocity method relies on the fact that a star does not remain completely stationary when it is orbited by a planet. A planet is much smaller than its star, but it still exerts a tiny gravitational pull or tug on the star as it orbits. When a planet is behind the star, from our point of view, it pulls the star slightly away from us. When it's in front, it pulls the star slightly toward us. This causes the star to wobble back and forth. Astronomers look for this wobbling to find planets. They use something called a spectrograph and powerful telescopes to examine the light coming from a star. A spectrograph, like a prism, splits the light from the star into its component colors, producing a spectrum. Some of the starlight gets absorbed as it passes through the star's atmosphere, and this produces small, dark gaps or lines in the spectrum. As the star moves closer to us, these lines shift toward the blue end of the spectrum. As the star moves away, the lines shift back toward the red end of the spectrum. So the spectrum appears first slightly blue shifted and then slightly red shifted. Therefore, astronomers can look for orbiting planets by looking for these back and forth motions of the lines in a star's spectrum.
And you can work out from the speed that's being pulled towards you and how long it takes to go around in that circle, you can work out the mass of the planet or the companion thing which is pulling it around. If that mass is very small, the thing is a planet. That method has been very successful. It found most of the planets which were discovered early on.
However, the Kepler technique was based on the planet's transit. The transit method is based on the observation of a star's small drop in brightness that occurs when the orbit of one of the star's planets passes. Transits in front of the star. The amount of light lost depends on the sizes of the star and the planet, and the duration of the transit depends on the planet's distance from the star and the star's mass.
With the Kepler Space Telescope, when we look at a star, we don't see the planet directly. All we see is a tiny dip in the brightness of the star when the planet passes in front of it. From the size of the dip, we can work out the relative size of the planet. Is it a big planet or is it a small planet?
The combination of transit photometry and Doppler velocimetry reveals planetary radius, mass, and density, which are some of the main parameters to evaluate the potentiality of the exoplanet as an Earth-like candidate, and so to harbor life.
Once you know the distance away from the star and you know how hot the star is, you can estimate what the temperature on the surface of the planet would be like.
Another of the main parameters to analyze the Earth-like potential of an exoplanet is its atmospheric composition. Atmospheric studies of exoplanets might be performed with spectroscopy during planetary transits. During the transit, the stellar light passes through the atmospheric limb of the planet. Spectral analysis of this filtered light reveals the structure and composition of the atmosphere. Astronomers could identify the most Earth-like exoplanets by detecting the biomarkers, which are the imprints that life forms have on their host planet atmosphere. For instance, the molecular oxygen that we are breathing results from the presence of life on Earth. Unfortunately, with present-day technology, it's extremely hard to closely study the atmospheric composition of those remote planets.
The main thing that's keeping us from being able to do that now, of course, is technology. We don't have the technology, in functioning instruments at the moment to be able to do that effectively. But that's something that will change with other missions in the pipeline, like Jack Webb Space Telescope and other missions that are happening.
Kepler continuously monitors over 100,000 stars similar to our Sun for brightness changes produced by planetary transits. Thanks to this ingenious technique, Kepler has confirmed to date more than 1,000 exoplanets. Scientists think that about a few dozen of them can be labeled as Earth-like. Considering the possibilities of finding an Earth-like exoplanet are much higher in the circumstellar habitable zone of its planetary system, the planet hunting then started to focus on those areas. One of the first discoveries was 70 Virginius b, an exoplanet located approximately 60 light-years away in the constellation of Virgo. 70 Virginius b was located exactly in the middle of the circumstellar habitable zone of its planetary system, so it was supposed not to be too hot or too cold. Unfortunately, further studies reported that this remote world was a gas giant with very high temperatures, which ruled out any potential for liquid water and therefore of life. The early findings were discouraging in terms of detecting an Earth analog. But this was just the beginning. In 1998, a discovery made in the star Gliese 876, a red dwarf located in the constellation of Aquarius at a distance of 15 light-years away from Earth, really encouraged astronomers. A gas giant was detected in its habitable zone, Gliese 876b. Three years later, another gas giant closer to this one was found, Gliese 876c. We know that life as we know it is not possible on gas giant planets such as Jupiter or Saturn. But the big surprise was that both exoplanets may have habitable moons orbiting around them, as Jupiter and Saturn have.
This was one of the first planets to be discovered in the habitable zone, and people theorized that if it had a moon around it, the moon would be rocky, and the moon would be the right temperature to have liquid water.
Why couldn't any of these hypothetical moons around Gliese 876b and c harbor life, as we hope Jupiter's moon Europa or Saturn's moons Titan and Enceladus might?
So it's an exciting place to think about, and maybe an exciting place to look for in the future.
After the discovery of these exoplanets with potential Earth-like moons, several similar exoplanets with moons orbiting around them were discovered. Maybe on any of those remote moons, life arose in the past, or exists in the present, or might appear in the future. After all these early discoveries, we started to approach to the main goal, to find the most Earth-like world. An Earth analog, also referred to as a twin Earth or Earth-like planet, is a planet or moon with environmental conditions similar to those found on the planet Earth. If life could arise on Earth millions of years ago, and if we look for exoplanets similar to our planet, the chances of finding habitable planets skyrocket. Recent discoveries have uncovered planets that are believed to be similar in many ways to Earth, with relatively high Earth similarity indexes. The size is often thought to be a significant factor, as planets of Earth size are thought more likely to be terrestrial in nature and be capable of retaining an Earth-like atmosphere.
From the point of view of Kepler, a planet is Earth-like if it's small enough that it's probably rocky. It's not a gas giant like Jupiter or Saturn.
But size alone is a poor measure, particularly in terms of habitability, because next to us, there is a planet with a very similar size and mass, Venus, where it is almost impossible for life to arise. There are other criteria to be considered, like the surface gravity or the star size and type.
A planet is Earth-like if it's the right distance away from its star that it's in the habitable zone, that it's not too close that it's too hot and all the water that it would have would boil away, and not so cold that if there was any water on it, it would all freeze to ice.
If we are able to examine all of these parameters of an exoplanet, we would be able to know if it is or not a real twin Earth.
So when we say Earth-like for Kepler, we usually just mean that it's small enough that we think that it's solid enough that you could stand on it, but that doesn't mean that it has an atmosphere or that it has an ocean.
It's also often cited that an Earth analog must be terrestrial. That is, it should possess a planetary surface composed of materials similar to Earth's. The conclusion would be that extrasolar planets, or moons, in the center of its circumstellar habitable zone, the so-called Goldilocks position, with substantial atmospheres, may possess oceans and water clouds like those on Earth. In addition to surface water, a true Earth analog would require a mix of oceans or lakes and areas not covered by water.
We believe that water is essential, but just about everything else you can think about, which is important for life, there seems to be life on the Earth that doesn't need it. There is life that survives without sunlight, there's life that survives without oxygen, there is life that survives deep down underneath the ice in Antarctica.
Unfortunately, with the present technology, we can't properly evaluate most of the parameters like the temperature, the atmospheric composition, or the surface of the exoplanets. Nevertheless, considering we have already discovered hundreds of exoplanets, we can't help but wonder if a real Earth analog has already been discovered. On 18th April 2013, astronomers from the Kepler team announced a discovery that created great expectation. For the first time ever, two very Earth-like exoplanets were found. They were the Kepler 62e and the Kepler 62f. And orbits Kepler 62, an orange dwarf star, in its circumstellar habitable zone. They immediately became prime candidates to host alien life. A modeling study also concluded that Kepler 62e and Kepler 62f are likely covered mostly, perhaps completely, in water. Kepler 62e probably has a very cloudy sky and is warm and humid all the way to the polar regions. Kepler 62f would be cooler, but still potentially life-friendly. Unfortunately, they are at a huge distance of 1,200 light-years away in the constellation of Lyra. Soon after, it was discovered an exoplanet even more similar to Earth, Kepler 186f. This finding was a milestone, as it was the first rocky planet found in the habitable zone of its system. It is 492 light-years away from the Earth.
Kepler 186f is possibly my favorite planet to come out of the Kepler mission. It's a small planet. It's maybe 10 to 20% bigger than the Earth. Based on everything we know about planets, it's almost certainly to be rocky. And it's the right distance away from its parent star that, if the atmosphere is right, if the greenhouse effect is right, it could have liquid water on the surface.
After that discovery, several more Earth-like candidates started to arise, like Kepler 438b, Kepler 442b, or Kepler 440b. All of them were very similar to our planet, but none of them was a real twin Earth. But everything changed on July 23, 2015. That day, NASA's Kepler Space Telescope science team shocked the scientific community with an amazing finding. The most Earth-like planet ever was discovered. Its name, Kepler 452b. What made different this one to the other previous Earth analog candidates? Kepler 452b is the very first, apparently rocky planet that orbits a G-type star like our Sun.
It's a planet in the habitable zone around a star which is almost a clone of our own Sun.
After this discovery, the Earth is a little less lonely in the universe. Kepler 452b circles its star, which is about as hot as our Sun, 10% brighter and 20% larger, at an orbital radius just 5% larger than that of the Earth. A year on this planet is 385 Earth days long, just 20 days longer than Earth's.
What makes this slightly less exciting from the point of view as could it be habitable is its size. Our best guess at the size is that it's about 60% bigger than our own Earth.
It is the smallest Earth analog planet ever found in the habitable zone of a G-type star like our Sun. Previous research on super Earth-sized planets like 452b suggests this one has a good chance of being rocky. If it is a rocky world, it'd weigh in at about 5 Earth masses, giving it a surface gravity of roughly 2 grams, which would mean that our weight would be double on its surface. Kepler 452b could have a thick, cloudy atmosphere and volcanic activity. Even more exciting than Kepler 452b's Earth-like demeanor is the fact that this world has spent around 6 billion years in the habitable zone of its star. That's considerable time for life to arise somewhere on its surface or in its oceans, should the conditions for life exist. Kepler 452b is about 1.5 billion years older than the Earth. If it was Earth-sized, the planet and its aging, brightening star might be at a point in their evolution where liquid water would be rapidly evaporating from the surface. But because of its higher mass, astronomers believe Kepler 452b could continue to hold liquid water for the next 500 million years or so. So far, it's the only known world in the system, which lies some 1,400 light-years away in the Cygnus constellation. Obviously, we're not going to get there anytime soon, but it's fascinating to imagine that far off in the distant reaches of space, a world very much like our own might already exist. If this twin Earth exists, why couldn't thousands more like it exist? Less than a year after the amazing finding of Kepler 452b, on May 2016, a new discovery shocked the scientific community. astronomers using telescopes at European Southern Observatory in Chile discovered 3 planets around a dim dwarf star just 40 light years from Earth in the constellation of Aquarius. These worlds may be the best targets so far found in the hunt for life elsewhere in the universe. They used the TRAPPIST telescope to monitor the brightness of an ultra-cool dwarf star in the constellation of Aquarius, which has been named TRAPPIST-1. TRAPPIST-1 is much cooler and redder than the Sun and barely larger than Jupiter. Stars like this are very common in the Milky Way, and they are very long-lived. This was the first time that planets have been found around one of them. The 3 planets are very similar in size to the Earth and might have habitable regions on their surfaces. But the really exciting result is that these are the first Earth-like planets that are well suited for the detection of life. The ultra-cool dwarf stars are the only places where life could be detected on an Earth-sized exoplanet using our current technology. The light from much brighter star, like the Sun, for example, would swamp vital measurements of the atmospheres of any candidate planets. The next step is to make more detailed observations using the next generation of telescopes, such as ESO's, European Extremely Large Telescope, and the James Webb Space Telescope. That will allow astronomers to study the atmospheres of planets like this and to search for molecules related to biological activity, like ozone, methane, or water. Although there is not yet any proof of the existence of life on all of these exoplanets that we've already found, even in the most Earth-like of them, like Kepler 452b, we can't help but wonder if any of those potential forms of life that might have arisen there were or will be able to evolve into intelligent life. If any of those extremely remote worlds was formed billions of years ago, as Earth did, and it became into a habitable planet, then the organic compound had time enough to mix up and organize into living forms. Perhaps any of those living forms might have evolved into complex forms of life, and some of those complex forms of life might evolve into intelligent beings with consciousness. Thanks to Kepler mission research, it's known that just in our galaxy, the Milky Way, there might be millions of Earth analogs, and there are billions of galaxies across the universe. So the chances are much higher than we could have ever imagined. For that reason, science is carrying out an intense search for intelligent life. The SETI Institute in California is nowadays the main world institution devoted to the search for extraterrestrial intelligence. Its name, SETI, stands for Search for Extraterrestrial Intelligence. This search is based on the use of radio telescopes. Radio telescopes receive radio waves. As we can't go to space aboard spacecrafts to find that intelligent life, what we look for are radio signals.
What we're looking for is a signal that's at one spot on the radio dial. Just like when you're listening to the radio in your car. You know, you tune across the dial, you hear static everywhere, and then at one spot you're near, and there's a station. Okay, that's the signal that's produced by a transmitter somewhere. It's not natural static. It's not like a quasar or a pulsar or galaxies or hot gas, cold gas. All those things in space make radio noise, but it's all over the dial. So we look for signals that are at one spot on the dial, and of course the source of the signal has to be up in the sky. Those are the kinds of criteria we use to know that even if we don't know what it means, we at least know they're there. They're on the air.
Unfortunately, till now, we haven't received a signal that can be really attributed to extraterrestrial intelligence. In the coming years, NASA and ESA, the European Space Agency, have planned to launch several space telescopes that will surely help to unveil the mystery of life beyond the boundaries of our solar system. The most ambitious one is the James Webb Space Telescope. This project is an international collaboration between NASA, ESA, and the Canadian Space Agency, CSA. It will be the premier observatory of the next decade, serving thousands of astronomers worldwide. It will study every phase in the history of our universe, ranging from the first luminous glows after the Big Bang to the formation of solar systems capable of supporting life on planets like Earth, to the evolution of our own solar system. This new telescope, 3 times more powerful than Hubble, will be able to analyze starlight passing through the atmospheres of the closest Earth-like worlds, looking for the telltale signs of life itself, like, for instance, detecting gases in its atmosphere usually linked to life processes such as oxygen, methane, carbon dioxide, or nitrogen.
JWST is really going to help us understand what atmospheres of planets are like under different conditions, and that's going to be a really exciting result.
There is another mission, the CHEOPS mission. CHEOPS comes from characterizing exoplanet satellite. This is an ESA mission dedicated to searching for exoplanetary transits by performing ultra-high precision photometry on bright stars already known to host planets. With all of these new space telescopes programmed to be launched in the coming years, we are sure that finding a habitable exoplanet and any consistent biosignature will be just a matter of time. If we are ever able to find evidence of the existence of any form of life among one of those billions of exoplanets we know are across the observable universe, it would be undoubtedly shocking.
If we did find life somewhere else in the solar system and we were able to do, for example, a genetic analysis to determine that it was distinct from life on Earth, that would be a really earth-shaking discovery.
Living generation might be witness of a finding that would undoubtedly be a turning point in the history of humankind. The discovery of life in outer space.